snapshot of any industrial city in the early 19th century. It used to look like this, including Bombay, where I stay now. It used to look like this. A lot of pollution, a lot of people, a siren going. You can just imagine. Close your eyes and imagine such a thing. Or some of you may recollect. And 18th century, slowly the manufacturing, third manufacturing was born. That is making not one but millions, right? The concept of interchangeability was also brought in. So you have a nut and a bolt, and somewhere nuts are made, bolts are made somewhere else, and they still work as nut and bolt when they are put together. So there is a disconnect between the end user and the manufacturer, and things were opportunities were identified and made. That's it. It was a maker's market or a seller's market. What do you call the capitalism and all those things was born those days. And you can see Ford. He was a very intelligent man. He just thought the carriage pulled by horses, after all, can be replaced by James Watt's engine, right? That's what he did. This is innovation. He did not invent anything. A horse cart was always available. He just removed the horses, and he put an engine there. And car was born. He is supposed to be the inventor of the car. Ford, and he also brought in a lot of reforms in production. He brought in what is known as a production line. What you see here, this looks like more like a cow shed than a production unit. You can see a lot of people in line doing a little bit on the car, what is supposed to become a car. So chassis enters on one end, so people start populating various components onto it, and finally they fix the four wheels and it will be wheeled out. The whole thing, the value chain, starting as just a chassis and holding on to so many components and becoming a complete car which runs. And this was a new way, production line, right? Even today, many companies, why car, not only car, but mixies or anything you take, they all have a production line, right? Production line is there, which will take care. And many of these were further improved by Japanese. See, Japanese were not making any car till the Second World War, where the whole of Japan was destroyed by bombing and all. They had a great problem of after World War effects. So they were not into making cars. Slowly, they learned everything. Then they ruled the world. Even today, they rule the world of automotive systems. Though they learned from Henry Ford. Later on came a journey of the computation, and people started trying out many things, like first adding and subtracting, multiplying, dividing numbers. What you see here is ZUs, or we call this is Z1, the first electromechanical calculator. It was very big. Today, what you have, you don't even have a calculator today. It is missing, right? Your calculator is missing. It is in your cell phone, hidden. Whenever you want, you can invoke it. So, electromechanical calculator was so huge. So people slowly started looking at many other development like radio valves. The valves were so big, and they led to another miniature form called transistor, which was also called as a solid state. because were annoyed with the so-called radio valves, which used to have a lot of ion cloud inside. It will take a lot of time to come up. So they said it is not a solid state. And, transistor became a solid state electronics, and there is no stopping, of technology from then onwards. That led to the miniaturization. Uh, then the so-called ICs came, the microprocessors came, and that's how the production technologies started deriving a lot of benefits from these electronics. Okay, and electronics laid the foundation for computing also. You know, and now coming to the connection, how this is connected to design. You know, design, it is connected because we have been solving problems, or the needs by ideating, and that's the human nature. From the beginning, uh, people had either problems, posed with a problem, or they had a need. Okay, and invariably these were met by some kind of intelligent planning. So that intelligent planning, we call it as design. Okay, so this particular course series, it is 3D printing and design. So I wanted to bring in some kind of design also in this, because it is this the problem or needs that drives the humans to work on whatever you call it, manufacturing you call it, design you call it, or you call as anything, as a craft also. They were all trying to solve a problem. You know, what people used to call it as craft, that became engineering, that became design later on. You know, but it remains same, solving a problem. Correct? No. For example, the pot what you had was holding water. It was holding grains. It was holding sometimes even the valuables. You know, they used to put it inside the earth. There were the safe packs, right? And so let us see how this problem is getting solved. So you have a set of Jenga blocks there, and I have a problem of crossing a river. I'm just giving an example here, and there is a way to cross the river, right? So design is an activity of finding solution. We call it as even a problem solving activity. Correct? No? Or coming out with solution. But not only these, the problem or the opportunity, the problem is also an opportunity. For example, if you take this example, we a heap of Jenga blocks, it can be simply made into a tower like what you have. It can also be put in different configuration, create different things, and that is the beauty of design. Okay, and the mankind has been working on this all the time. That's why we call, there is nothing called as a best design. There is always a better design to come. Correct? No, there is nothing called best design. No, I don't say my presentation is best, because I keep working on it. Every time I work on it, because I'm not satisfied. This is also human nature. Not so. Our human wants are unlimited. This is a kind of a economic axiom. They say human wants are unlimited. And Mahatma Gandhi said there is a solution for every need, and there is no solution for the greed of humans, like that, something like that. So this process of finding out solutions, finding out need, opportunities, and synthesizing it is what we call as design. And this is simply bringing ideas to life. You may have a bright idea, but people have been trying to bring ideas to life. And how it is done? In industry, we do it by actually iterating or thinking of or envisioning many things. You know, we take out the mind's picture on a paper and throw it around, and they also contribute. You know, and we come out and try out many things before we actually go and make a product, right? And this is in fact captured by a systematic way by which we can produce products and solutions, be it a tangible or intangible product. Invariably, we go into these blocks. What we used to call during our design school days, used to call it a design methodology. And today it has got a glorious new name called design thinking. Okay. But design thinking to design methodology, there is a small difference. That is, they bring, uh, they bring the business aspects also when you talk of design thinking. Okay. Whereas in design methodology, we don't really look at the business side of it. So it has got an idea which is generated, it's got synthesis, then with a set of criteria, we are going to screen it, and then we go into detailed design, the nuts and bolts of design, and then invariably every idea has to be tested, and testing is better done with a model, okay, and that's called as a prototype, okay. There are different types of prototypes one can think of, and then we are going to launch it. That's how this process is called as a new product development, and it is being used all the time, in all the industry, even today. Whatever you call it a design thinking, more glamorous name, and but these are the pillars by which we do. And in fact, why ideas have to be tested? Because the cost committed curve and cost incurred curve,
Then I
are
will transfer
different.
now only.
That means
By evening
I
you
can
send the
sit
emails.
quietly here in a room
I will transfer the
and
money in
ideate anything,
another 15-20
think
minutes.
of anything in the world.
Hmm?
Correct, no?
Okay.
It doesn't really require so much investment, some time, that's all. Or you go to a coffee board, a tea board, take out a paper napkin
Hmm?
and draw something, on the dining table, and that
And link
becomes a
customer what
concept
customer?
design, right? And
Only the last
then you
thing
can
is
go back to a computer
ಯಾರು help ಇಲ್ಲ.
or a drawing board. During our days, the drawing board, we used to draw things, and then again, there should be a dialogue between us and the paper, you know. Then with the others, they all used to contribute. Design is a group activity. It's never uh, only one designer sitting and doing. If at all it does, there is a user and a you as a designer. There are always two people, but there is somebody who is financing it, and somebody may help you with a lot of other tasks which you cannot do. So it's always a group activity. And you can see when it becomes more detailed, making and all, you require a lot of help. That's where the price, the cost will increase, and so the cost incurred blue curve is very very small. Uh, when it is going, cost is low, and it goes steeply up, and it reaches the um, complete expenditure there, 100%. So orange curve is the curve which people are really people who fund you, or the company, or your boss, or the organization will be worried about how much to actually invest into it. If you're thinking of some product, I want to bring out something, how much it will cost, when and all we have to pay these in different phases. So, supposing you find that idea doesn't work, then all the things what you have so far invested will go down the drain, right? And so it becomes very important that every idea is better tested, you know, than actually investing into it. So idea testing is never easy, you know. People have been doing it using prototypes, right? And validation, we call it as proof of concept, POC. And further, if you make it little sellable first product, we call it as minimum viable product. Correct, no? Minimum viable product. Well, we'll not go deep into it, but the prototype itself, has various roles to play in the development of a design. So planning, concept development, system level design, detail design, testing refinement, production ramp up. Each one have their own emphasis of the requirement of prototypes. For example, in concept development, there are 2 stars. That requires there is a merit using prototypes there. In system level design, it's only 1 star, so less emphasis. And you can see here, testing and refinement, there is a maximum number of stars, there are 3 stars. Why? Because idea can be easily copied, and if you bring the idea to market, people can easily copy it. So how we are going to benefit from that? So ideas are highly contagious. Okay, supposing your idea is half baked, you bring it into market, you find that somebody will copy it, and not only just copy, they improve upon it, and they will get a better sales than you. So it is very important for the companies when they are trying to make products and sell them and create wealth to be conscious of this. So they need to make a product which is always going to win. It doesn't give any scope for the others to copy and improve on it. So they do a lot of testing and refinement, and that's where world over people have been using prototypes to lagatar testing and refining, test it and refine. If at all it fails, it has to fail in your idea kitchen. It has to fail in your R&D, right? If it fails in marketplace, who is going to benefit? It is the it is the competitor, not the end user. End users are, after all, they don't know you are bringing a new product. After all, they are most tolerant people, all the time. Customer is always a tolerant person, but the most dangerous is the competition, who are out there to copy your idea and improve upon it and bring out a new product. That is very important, and that's where it has become very important for us to make a idea like a POC or minimum viable product and test it lagatar. So if somebody wants to bring out a product, you're not going to launch with one version. You keep 10 versions with you and bring out the first version. So somebody will be busy copying it. Then you bring out the second version. Again, they will start copying that. You bring the third version. So a continuous improvement has to go on and on. Just like your software versions, products also have versions. They have features which are going to be introduced. It is a marketing decision when to incorporate what. So they want the market to copy, and when they copy, busy selling it, they are going to bring a new one, a better product, and that's how some of the market leaders are always selling their products. They maintain the market leadership that way. Okay, and so prototype, you see, very important in this process. And in fact, the early days, we used to do it all by hand. So when you do something by hand, be it a sketching or painting or a model, you need a lot of skill, you know. And either you need to have skill or you have to employ somebody who has got the skill, like model makers and all. If you are not able to make a pottery, you have to go for a potter, and commission him. If you are the person who is got a company to produce pottery, you have to hire those guys, potters, right? So you can see there are a lot of photographs here which show how we used to make prototypes in the beginning, in the early days, using clay or a puff or a cardboard, or in electronics and all, we used to actually connect all of them on a breadboard, rig it up, and check whether it all works. Most of the time, it doesn't work. Then you have a great opportunity to know what exactly went wrong those days. And you have then real life material like a monitor or a joystick or a button and some cardboards. You put them together, you're toying with the idea. In fact, design is a creative play. You know, Yesterday I was listening to one program. It was between 5 to 6, where Philip designer said, "Design is a creative play," and so it's very important. And these are the ones which need a lot of skills. Okay, So in a way, it was constrained. It was not easily. You just think of if you don't have a PowerPoint as software, what we find today, people used to draw everything in order to, and the board used to scroll up and down. Can you see? So they used to write it down, and everything is beforehand. So many people, and finally, when during the presentation, only a small window is opened up, so it rolls. That's how people used to do before. The world has changed a lot. That is the beauty, and it's all because of the computing power. With the computing power, luckily, we can do so many things. We can do virtual visualization. We can do virtual testing. We can check the kinematics by kind of animation of the gear mechanism, if you want, meshing of that. But all these are fine. But when you go and say the boss or the organization that, well, I have a product which perfectly works well on my computer, you fund me. So nobody will be willing to fund it. Why? Because they don't know how it works really. No, there are a lot of things which are virtual, which are going to work inside, but how it works in real world. So a real model is very much important. A prototype which can be held in hand, explode, make it run, check the functionality, etc. Very, very important. So time to market always were constrained by making a prototype. That used to take a lot of time, you know, and convincing the management to get the funding is also quite painful, and it used to take a lot of time. Today, luckily, uh, it is possible to create such ideas quickly on a virtual environment and get it going with various phases, quickly. And thanks to the technology, what we are going to discuss deeply, the 3D printing or additive manufacturing, it has made our lives easy, not to depend on the skill of hand making. You know, hand skills are not required. If you can do entity on computer, you can as well believe that it is possible to make it. Who will make it? A robot will make it, and that robot is called as 3D, or it could be a CNC, whatever, or a hybrid, right? So digitization of manufacturing has been happening quite some time, and with the microelectronics and computing power, today we are dreaming to a new order, right? That is Industry 4.0. You know, you can see how the world has moved, and catching up these technologies, transformation of energies. Now today we are in a kind of ICT revolution, and it is pushing to at the crossroads of what is called as Industry 4.0, right? Where everything is taken for granted. Communication, you know, all time uh, communication is possible, right? All time connection is possible, and all time availability of data is possible. All these are possible because of the ICT revolution. And today we are talking of big data analytics, cloud computing, Internet of Things, blockchain, and so many things. And even the virtual side also, AR, VR, mixed reality, and all have come. Uh, Together, they are making the digitization of manufacturing, and we are focusing more on rather the third industrial revolution. That is one of them is 3D printing, right? And so, if you look at the trajectory of the development, what was numerically controlled became a CNC numerically controlled with the advent of computing. And slowly they started with the CAD, computer aided drafting, just to draw and copy and mirror, etc. Only those commands were there earlier. Today, CAD, which is a bigger CAD, the computer aided design became a very important tool in the hands of a designer, because they not only sketch, they can analyze it, they can take the volume property, they can fill the color and texture, whatnot, everything. It's almost we can validate a design on a computer today. That is the big cap. You know. Then you have computer manufacturing, then MRP1, MRP2, the product data management, computer computer aided engineering, and there was then enterprise resource planning to make things faster and faster. Supply chain, mostly ERP was looking at the supply chain and the cash. It somehow it neglected design in the whole process. But design is so important. Design is a seed. It starts the whole thing, right? And so PLM started looking at that, you know. So it added PDM and ERP on both the sides, and it now today has a new avatar called PLM, and the PLM is further leading to Industry 4.0. You can see there is a steady digitization that is happening, you know, with the capability of tools what we have, you know, hands. And so you can see the world today is, you cannot think of the world without uh, communications, connected and as well as unconnected, correct, no? And today you cannot you wake up and check the, you know, WhatsApp, whatever, you know, status, whatever you're using, uh, without which we cannot even think of anything. Day doesn't start without these, correct, no? In a pandemic situation, the crisis which is going on today, this came to our rescue actually. This became a source of communication, keeping in touch. I'm able to reach all of you in your homes or in your institutes today, thanks to the ICT revolution. It is not only electronics, it is also the communication, which is high-speed communication that is going on. I'm not sure, some of you might be having problems, but today the smart cities or the those are all becoming, you know, a reality, you know, steadily. Moving forward, it's very important to know whatever we have, at the end of the day, we need to create products to enjoy the benefits, correct, no? And we have to make things. And so we call it as art of making things. The humans not only started with pottery, but they're today trying to jump to the uh, cosmos, from moon to Mars and beyond, correct, no? People may even visit Titan, the Earth-like satellite to Saturn, you know. People are planning. All this requires a lot of things to be made, things which will move, defy the so-called speed of light, because light years you have to travel. How can you do that? And so the art of making things led to a lot of mechanization, and today the subtractive manufacturing, which had the speed of cut, depth of cut, you know, all this, tons of material removal. Uh, well, this is a way the industrial revolution till now, recently, it was all doing done this way. Even today, for example, about 80-90% gets done like this. No? Either it is injection molding or die casting, forging, rolling, all such mechanized mass production processes, CNC, okay. But all these were not very economical. A lot of energy goes into it. A lot of material is removed, not added. So this was a big problem, and people started looking at options. They came out with a new option, additive manufacturing, okay, which is going to kind of solve these problems. So you can see the comparative, uh, uh, they produce less scrap and less energy. They add instead of subtraction, right? And today, it is a new regime where with a virtual model, you can convert that into a physical model. Transformation of CAD to part, very important. And it is today possible. You can think of uh, even unthinkable things, which were hitherto were not possible to make, possible to, um, uh, yeah. They used to say, don't think about it because you cannot make it. So it kind of brought a strict grammar into manufacturing. Okay, there's a rule bound design, what to do, what not to do. Design for that, design for this, design for X, all that. Today, people are actually looking at a new way that is designed for additive manufacturing. We have to unlearn all the things of 100 years and think of a new way. With this kind of technology, how can you design? I cannot take an existing component, say, I'm going to 3D print it. That is a really stupid way. We have to optimize it to this new process. How do you do that? That is designed for additive manufacturing. So it is basically art to part transformation. If you have a sketch, you can virtually do it. You can render it on a computer, and actually you can get to hold it in hand and explore. Very important. So 3D printing is a new way of making things, and it is a process by which we build it layer upon layer, just like the sandwich. The beauty of it is every layer I can start playing around with. Just like how you can play around with a sandwich, what content to fill in products also, you can play with that. That has given a lot of capability, including the microelectronics. Microelectronics, many of you don't know, it is like a 3D printing only. That's how the chip is made, layer upon layer. And 3D printing has the two main advantages, uh, main features actually. One is an advantage, one is a disadvantage. One is you can just about make any complex part, using 3D printing, whether it is in metal or non-metal. But producing in large numbers, like 1 million pieces or 10 million pieces, in a fraction of second, is not possible. That is what we call as the economy of scale. It normally, I keep asking people, what will be the cap of a Bisleri bottle will cost? Some people say 5 paisa, 6 paisa, 10 paisa, like that. They say it is a quarter paisa. Though there is no quarter paisa, but I'm just telling the value. Why? Because they produce millions. But if I want to 3D print that, that will cost a lot of money. Okay, so there is no economy of scale. Is one, little bit costly, and what is the advantage? You get complexity comes of it. So how can we really imagine this? So let us see. See this animation. You will see how the cost curve increases in the conventional manufacturing, how it remains constant in a additive manufacturing. And also you see how the wastage, there is a little wastage in additive manufacturing, but a lot of wastage. As and when you remove material, the wastage keeps increasing in the conventional manufacturing. Please explore this. So the 3D printing has come a long way. While we are going to go into the technology deep dive tomorrow, I'm taking you through a very gross route wherein we are going to come to some of the gross understanding of the subject. Okay. So in the early days, 1986 to almost 2000, we used to make only prototypes, mock-up model. Mock-up means It is not even a complete product. It looks like that. A cell phone you see, it's an early hand phone, which had no screen doesn't work, the buttons won't work. If you take out and see, it's all solid inside. That's called as a mock-up model. So people in marketing and all, they used to use it for a kind of a aesthetic approval of a product. A little later, with the technology becoming better, the tolerances becoming closer, they used to make things which are for design validation. What is design validation? For example, you have a headphone, headlight of a motor vehicle. What they used to do, they'll make a prototype, they fix it on the vehicle, okay, and run it for some 15 days to 3 months. And if there is a failure anywhere, it is a great opportunity. They used to be really happy to see where the failure occurred so that they can go back to drawing board and correct it. And if it doesn't fail also, they used to be very happy. Why? Because after all, the design is validated. Correct, no? Even today, every single piece, which is requiring such thing, they go for prototyping route with a better and better material close to the end user part. In 2016 to today, with the new technologies coming, with the processors and the capabilities of the new built material, we have what is known as making end user part. Making end user part, yes. So end user part, that means you are making a prototype and you can sell it. It has got a life cycle. And today's life cycles are shorter compared to the earlier days. I was asking somebody, what is how long you change your smartphone? They said 1 year. I changed. I don't want to change. I don't want to change for years, but somehow technologies keep becoming obsolete. You're forced to buy a new phone. So today, even for a guy who doesn't want to change, he will change it in 2 years. And that is the life cycle. And today, many parts what we make are end user parts. They are not the prototypes. They are not the mock-ups. That's where the whole technology is moving. And you can see, all said and done, where exactly 3D printing lies, the power of 3D printing lies. In high volume, still the vacuum casting, the injection molding, the investment casting, CNC machining, and all will take, depending on the volume, they have their own place in the market. 3D printing comes if the low volume and high complexity area. 3D printing is the only tech which is going to give you the solution. This is where rightly it stays. But this may change. This may start, flowing down to other. But volumes is a problem. Now let us look at the entire landscape. 3D printing is not alone. In order to bring any product out, we all know idea is so important. Idea which is getting translated, solving a problem or meeting a need, addressing a need is very important. Then you have CAD, which is a kind of creating virtual models, is also very important part, without which you cannot 3D printing anything. 3D print anything. So in between you have something called as pre-processing. So the CAD has to be modified such a way that you are going to make it ready for 3D printing, printable file. So there are conditions like water tightness or particular file format like STL or AMF or TMF, all those things. 3D printing itself as a system requires a lot of maintenance and care. It requires raw material to flow in, and then comes the post-processing. Post-processing is also very important. Everything which goes under the other conventional process also need to go for post-processing. So also 3D printed objects. And then that opens up a world of opportunity. That's what this slide tells. And today, there are a lot of content creators which are important. For example, for CAD, with a lot of solution for parametric design, like what you see here. For digital sculpting, there are a lot of things available. And for fun, makers, hobbyists, there are a lot of things which are available free. I'm sure you'll be learning all this, many of them, in the due course of this workshop. And we also have things which will try to improve the CAD output. NetFab is one software, or you have Materialize is another software, where they use it for file repair, slicing of the files, support generation, file exchange, or file size reduction, or incorporating textures and many more. And even analysis is being done by using these softwares. Then comes 3D content. Somebody has to protect it. Otherwise, people can chori kar sakte. After all, it can be sent on email. So if somebody has worked on it for years, designing, making it, working on CAD and all, once it is exported, it can be copied with a fraction of a second, or depending on the file size, it can be copied. It can be just transported at the speed of light. Okay, so that's where file protection and file tracking, file licensing becomes important. So there are many software solutions that are there. One is the limited edition object, what you call Leolane. The other one is Tized. But there are many more such solutions available. I'm not a marketing agent to them, but just for your information I'm giving, right? And so this is also very important. So this is what we call as ecosystem. 3D printing needs the content creation, content processing, content, 3D printing itself, and post-processing, all this. And safety, file security is also very important, which we are seeing now. And so, how can we summarize the so-called 3D printing opportunities? What are the goodness of this technology for us to use? One is part consolidation. Part consolidation means if a if a product is made up of number of parts, probably we can reduce the number of parts, make it, if possible, one part. That's called as part consolidation. So if you take a simple box, if I want to make the box lockable, on one side I need to put two hinges. The hinge itself has one part on the top, one part in the bottom, that has to be secured by screws. You see, so many parts to it. On the other side, you need to have a buckle to close it. Then you have a padlock, and you need to have those are riveted. Just imagine a simple box can have easily some 20-30 parts. Correct? No? But today, it's possible to make all of it as one part. Export as a CAD and get it printed as one part. Still they move, still they function like normal box. Still it is lockable. Still they have a hinge and open and closing is possible. That's called as a part consolidation. Then we have jigs and fixtures. Today electronics and many other technologies are becoming, every day they change. If it is a small, big PCB, it becomes a small PCB next day, or maybe in a couple of weeks. There's no point in making a metallic and one which will last for 30 years kind of jigs and fixtures, which are used for cars. And for Ambassador car, it is believed they had only 2 set of mounts. They used it for 30 years. Today it is not so. So jigs and fixtures on demand, we can make it matter of half an hour to 1 hour. We can make a new one. You just sketch it and make it on computer and fire it. You get it in 1 hour, like that. Need for lightweighting is another opportunity. Why lightweighting is required? Particularly for airborne systems like aeroplane, rocketry, satellite and all, weight becomes very important because the payload, what you call, every gram which is airborne is going to cost you so much of money because it has to be put into the orbit by actually flying up against gravity. That takes a lot of energy, right? So making it lighter actually helps you to carry a payload which is required, not which is not required. Like a dead weight means it's not required. For strength, what is required is it's just enough. So people are looking at kind of a lightweighting by uh, making it with a kind of a lattice structure, right? And that is becoming very important. In the car and all, it is not so much important. But with EV opportunities, even car makers are looking at this lightweighting in the car making also, because the e-vehicles have a battery. Okay, battery fully charged is also of same weight as a fully discharged battery. So that becomes a kind of a thing which is not there in the current conventional cars. The fuel tank, as you consume fuel, the tank becomes empty. At least, it gives some kind of a greater mileage because whole system weight will come down. But in a e-vehicle, battery weight is there. You stay put with it, right? So lightweighting becomes a very important thing even for the terrestrial vehicles in case of EV. Complexity is something which is, as you know, is the greatest virtue by which you can achieve using additive manufacturing or 3D printing. So like jewelry is what you see here. And a need for one part. Supposing somebody commissions just one, you know, I want to make a bust of myself. I want to celebrate with my, or I want to make a dummy, you know, for a mask, for a play, or for a filmmaker, something like that. Even for animation and all, people make miniatures, you know, of people, of building, of various things. Then also you require just one part, not many. So manufacturing is for millions, and 3D printing is for one part. So it has got agility by which you can make it and still you are profitable by making one part. So need for one part is another opportunity. Need for customization. What is tailor made is customized. You can today customize everything. What is customized normally? Mass customization, your spectacles. Spectacle frame is made. You are choosing a frame which is already made by conventional manufacturing, whatever. And even the only the glass are custom made, the ground and cut and fitted, the frame what you need. So today, that can be a very good example, but it is not 3D printed right now. People are actually thinking of that also. But customization is maximum in medical, or in future, people are looking for more and more customization. You know, the persona of the people, a child born today would be much different what they need. Well, moving forward, today 3D printing comes in all shapes and sizes. They're not just one. Each technology has its own beauty, its own capability and limitation. So that way we have got a whole lot of things at Imaginarium. And prototyping is all about bringing ideas to life. And we have been using 3D printing for making a lot of prototypes. Like this one, what you see here. It's a very small one made for kind of look and feel. One cannot sit on this because it is a small model. Okay. And we have also made things which are very big. This is a car which is 3D printed. Many of the parts are 3D printed by Imaginarium. Designer is Wazirani. Wazirani's Shul. Shul is the name of this. And here we made a lot of parts which are there, like the mirror, the glass, the rim of the wheels. Many of it is made by imaginators. This car doesn't work. I mean, it's not a fully functional car. They are working on it, interiors now. And so people have been, trying to incorporate the capability of 3D printing in many different ways. And you can see here how the pick and place capability is used by a complement mechanism. What we used to use it, the Borden tube, where हवा अंदर जाते तो वो लंबा होते, so that has been used here in order to make a pick and place actuator for a robot. Correct, no? Very important. In fact, the capabilities of complexity has pushed the market to explore new ways of making things and the emergence of new aesthetics, which will be valued. When we say that, we can say unimaginable designs or impossible designs can be made today. Like what? Like these. These are truly unimaginable material, is metal and designs. Nobody would have thought about it. It's all generated by a mathematical formula. Correct, no? You substitute n is equal to 1, 2, 3 and see what happens on the screen. Whenever there is an interesting form, you export that as a file. Send it to your 3D printer. It will print. Right, no? That is the beauty of this. You can see this is also done that way. It is studded. It's made in gold. Studded with diamonds. Goes as a, a kind of pendant. We'll see this later. You can see this elephant. This cannot be injection molded, rolled, or CNC milled, right? Only 3D printable. Lot of such opportunity. A pottery. Again, it is not possible to make such things because you cannot remove the core inside. Only 3D printable. See this one. Can we?
Hello, Dr. Group sir, you have to unmute yourself. You're not audible.
How long it has been like this?
Then just few minutes, two slides back. You can go back to the previous slide. That's it.
Okay. No, I was annoyed with somebody.
Some sound.
Yeah. So these are all some flexible.
You show the gold pendant, from that slide.
Oh, I see. I see. Okay.
That's it. This is the place.
Okay. This is
Thank
very.
you.
No problem. So you have this. No, this cannot be injection molded. And again, here is a pottery. We cannot injection mold this because undercut. And you find this lights. You cannot see the light here. You are seeing the effect of light. So beautifully done. Again, not injection moldable. See this one, or a chalk piece like, making design, you can use any type of design. This is a footwear. Again, it's a flexible one. Again, this has got a mixture of a hard bottom, soft top, by which you can wear this shoe. This is also again same type of thing, capability. The bag, all printed using a powder. Again, here you can see these are not from Mount Abu or Belu Halebi. They are mathematical formulas which are mirrored and printed. So it's a very nice thing. Tomorrow's habitats, we thought. And force fitting the animal and furniture, what all you can get. You can get a lot of things like this. There's always a market for all this, and these are all 3D printed, right? And so the capability of making these kind of shells, which are only seen in the nature, if you magnify a cotton wool, you see some such structures, and which is found only in nature. So we are able to make such things. These are all diamond crystals, like forms, which are intertwining and making a necklace there. You can see the fluidity of a scarf going around like a cloth or a silk is actually 3D printed. And it is flexible. People can make a lot of these customized gifts also. Gold plating can be done. You can incorporate your initials, or you can have a moving gears. These are all phone cases, and that's all possible. You can see here these assembly is possible. It is exported as a full CAD into the 3D printer, and it prints it as assembled condition. Okay. The left hand side is made of silver. It is studded with diamonds or CZ. It is enameled also. Okay, these are all post processing done. And we have a necklace which is white in color but pigmented as pink on the right hand side. You can see it is all connected but printed as one. You can have a lot of such varieties you can have. And you can see here how these mementos are made, golden, silver and copper, quickly. And again, this cannot be easily injection molded, because of the lattice structure what you see. And some of these are artifacts which have capability of even having the IoT connection, which are brought about by the beauty of 3D printing. And you can see here how this can be also rotated, and it looks like a artifact in the morning when people see it like a vase. Night it transforms into a light. And today, jewelry is not a piece of gold; it is a piece of fun, it's a piece of attitude, and you freak out with the design. Good, isn't it? Reimagining jewelry as an artifact, purely having fun. You can see here how a resin is printed and that is converted into a gold or silver, platinum, after cleaning it. So first what you see, the purple color is the one that is printed, it is a printed resin. Through lost wax process, we do these transformations into metal. And after that, it is studded, right? So design will lead the consumption in future. Manufacturing will be taken for granted. So manufacturing, that's what is going to happen with the digitization. And the future of 3D printing itself is moving beyond prototyping to making end user parts. With HP, they brought in a game-changing technology which is going to challenge the injection molding. That means today I can make an injection molded part, just one. Can you imagine? So we don't call it as a injection molding, we call it as moldless production. Correct? No? 3D printing is called as moldless production also. So here you can see It can bring speed, quality, and cost, all at once. Further, we can also embed intelligence and electronics inside, that the work is going on. And to make multiples, you don't have to have a metal mold now. You can always go for a small batch production, vacuum gas mold using silicon, and you find that is done doable in a kind of 6 to 8 hours time, and within a day we can create multiple copies. That is the beauty of it. So what is the process? You 3D print the model, uh, you finish it as a master pattern, then create a mold which is room using room temperature vulcanizing. Then you cut it open and you have a mold with you. When you take out the master, the cavity left behind is the mold, and then you can use that mold to create a few samples, 20, 30, 40, like that, quickly. So this is a rapid tool, what we call. Rapid tool can be a soft tool, it could also be a metal tool. People use it in a different context, different names, but this can also be called as a rapid tool. And what's more, this technology gives you a lot of geometric freedom, as we can see here. And it is possible to incorporate artificial intelligence and all that kind of optimization to make things which are optimized for a particular um, constraint or a context. Like this particular component is optimized, you know, and once it becomes optimized, the only way we can produce that is by 3D printing, because it becomes more and more organic uh, from a crystalline or block-like thing, which can be machined to more organic form, which is optimized. In fact, the whole design itself as a discipline will follow a different routine in future. So you have a condition, you have to specify, for example, if you take a chair, uh, what is the function? You are going to define what is the weight of the person, you define, maximum, minimum, and all that. With that, you give it to the artificial intelligence. They start looking at various optimum solutions. They throw at you different solutions. So designer's job would be to validate it, recheck it, and curate it. And so a lot of things, that's what designers will do. So better take care to learn these, very important. That should be part of the design discipline. And a lot of things, nature is the best designer. So better look at the nature and produce things. And even that, people are able to do better using 3D printing. For example, looking at Huddy, optimizing it, for compression as well as tension, for shear, for the loading. So functionally graded materials are coming, which again throws up a lot of new things, which are only 3D printable. You can see how the transformation happens. We have seen by animation, and people are trying to see how to go about doing things. A lot of papers coming. Uh, One of them says about looking at function, constraints, objective, and free variables for which you can play around and get iterations, valid solutions. And people are also looking at, like you have all the constraints, also solution, give it a expert system that will give out the solution out. So people are looking at some kind of automation in design, and which can go define things which you cannot even imagine what will be the output of a DFM, a process. Okay, and this has become more and more uh, increased area of research, where people are looking at. So if you really look at things, the opportunities, the one size fits all kind of thing is only fit for the last industrial revolution. Today people are looking at the customization, the personalization, and going to bespoke products which are one-off, made only for an individual, will fetch more value that we can have. Modularity is a middle way. A lot of modular things people are thinking of. Modularity brings in a greenness also, because we are able to reuse, recycle and reduce, production by modular approach. Okay, and so a lot of things are going on in this area, which will be really interesting. I want to show you some of the capabilities this technology brings. You see, this is a FDM, but you will see the snout is very hard like a rock, while the body is flexing because of the structure it is made up of, right? Because of the thickness, it can flex. So some of these are very important capabilities. This is like a rubber, so it is able to, we can press it, and it comes back to its original set. You can see this is a compliant mechanism by which I can use it like a spanner, right? And there's no moving parts, no joints, right? And it is fit to the function, where it is required. So they are able to use it. They are able to again use it for opening, closing. Okay, you can see this again a compliant mechanism. The whole thing is printed as one because of the structure and its configuration. Some areas work like a 4-bar chain, okay, and some act like a solid block, and you can see how it works. Again, these are not possible to injection mold. Probably you can injection mold it if it is a simpler form, probably. And the biosystems. So people are increasingly simulating many things by which we can make, this is like, for example, a heart model. And in fact, we had made one at IIT Bombay, which I can probably show it tomorrow, where we did a different kind. So such things are also possible thanks to the technology. And you can see here, the capability of technology brings in a lot of things which will make so-called physical things also come alive, where you have an very interesting interaction, like this, which is closing. And also, a lot of things which are jewelry, for example. This was made at Imaginarium. Aina is a smart ring by which you can make payments, you can take phone calls and all, by gestures and all. If you look closely on the right hand side, there is a display which is coming on the top of the ring. Though it may look like a ring, it is actually a very smart device. It's supposed to be the world's first AI powered finger ring. Okay, it was made at Imaginary. And this designer, Apurv Shankar, happens to be my junior from IIC, and he is a Mumbaite. I'm so proud that we could make it, And Apurv, we look forward to more such innovations from him. And mass customization is another area which this is going to bring in. And you can see here the Gillette blade. Blade is not mass customized, but the handle can be mass customized. People can order it. That is the beauty of it. Today we can call it as a democratization of design, because people can actually play on a gamification interface, create their own designs, and get it made. That's why I said designing is very important. Manufacturing will take a backseat. They can depend on a cloud factory, like what you see. The whole thing will be done in future with a hybrid form. The CNC, the robots, the 3D printers come together, make everything what you need for the world. be it clothing, be it food, be it drugs, be it your car, anything. So the whole thing will reduce to a box like this, where you interact, from outside using IIoT and ICT technologies and the blockchain to track the traceability of material and supply chain. All that will come. That is the beauty of the whole thing. This is the cloud factory concept of cloud factory. We already built a cloud factory in the year 2018, and it has been tested. In the pandemic time, we never actually were anticipating something like that will happen. But thanks to this cloud factory concept, we were able to actually cater to our customers because of this concept, wherein people can upload their file and get it delivered to their doorstep. That is the beauty. So looking at product design itself, the study digitization has brought in large parts have become smaller and smaller. At one point, they disappeared altogether. They disappeared because, you see, camera, what you have is not there today. The music today, as a standalone, you don't have, everything of these hardware, what you have, they've all come to smartphone as one. Your computer is not required. Smartphone, camera is not required. In a way, the product is becoming invisible. Correct? No? They're all going as apps now. That will take care. So that is the beauty of how the transformation is happening. While some of them have to be physical, and like for example, smartphone has to be a physical smartphone. It cannot become virtual, but it can become smaller and smaller, so much that it may be wearable one time. At some time it may become wearable. It may be put in your ear, or I don't know. It may be fixed here with the brain, like what Teslas are trying out. Correct? No, you know about that. So that's how the digitization of manufacturing is happening. I think with this we come to the end of the today's presentation. I'm sorry, some logos are getting cut, but this is my our website www.imaginum.io. You can reach me at gp@imaginum.io or this phone. I'd be happy to take your questions now. I would like to stop presenting here at this point of time. How do I?
Yeah,
Stop.
you
Say,
just
stop
go.
sharing.
Yeah.
And so we are now open to questions.
Yes.
Hope we have come to the full time I've utilized.
Yes.
It is a couple of minutes, but I'm ready to stay for longer if anyone has an interesting question.
Yeah.
Hello, thank you, Dr. Guru Prasad Rao-ji. I'm Dr. Ramachandran from PhD College of Technology, Coimbatore, Tamil Nadu. Basically, I'm a textile and fashion technologist. I'm quite delighted to see that you have made a lot of design-related products in respect to jewelry and accessory items. It was quite interesting. The thing I just want to ask you is, what kind of material can be used for making a flexible product? And what is the best suited technology for making the product? For example, like textile, fabric kind of a product, if you want to take, what could be the suitable raw material that can be used, or any kind of polymer which is used in used for 3D printing can be used, or you have any specific kind of material for making a flexible product out of that? And I also want to tell you the technology. We have a lot of technologies, right? We have powder technology, solid base, and liquid base, resin based technologies all these days. Which technology can be best suitable for making a textile substrate kind of material?
Well, very good, interesting question. Thank you, Professor Ramchandran. And PhD is very. I have visited PhD many times.
Oh.
And in fact, PhD has a very good center also. There is one friend of mine who handles it, Sridhar Kumar.
Yeah, Sridhar is looking care for the Tefacor and
Perfect. Yeah, yeah. That maintains a very good center also.
yes.
Well, coming to your question, I am a fan of this technology, so I don't discriminate on material. I like the hard material, I like the powder, I like the resin, I like the biomaterial, I like all of them because all of them have their own space where they're applicable. Now, coming to textiles in particular, people have tried to print kind of uh, things what we used to do earlier, the early days, Tipu Sultan and those time, people used to have some kind of a metallic jacket which was made up of rings.
Yes.
Today it is possible to make that, that kind of jacket, which can withstand the hardship of a knife or a sword fate, but it cannot take care of your so-called bullet thing. So bulletproof also, people are able to use caviar and other material and also carbon fiber to do textiles. Okay, people have tried to do flexible material like resins can be used, bio-based can be used like PLA. People have used polymers to print various things. So small things which are hard, if they are reticulated, can act like a cloth. Okay,
Okay.
I'm going to show it tomorrow because tomorrow I'm speaking about deep dive of technology and also applications. I think tomorrow you'll be able to see, but it can be answered in two ways. One, making a flexible material is one, and keeping it hard but making it to a flexible thing by reticulation or articulation is another methodology by which we can do this. Okay, but very important thing, 3D printing, why you want to use, why today's clothes are not okay, you're not, you're unhappy, is a question. See, for any application, no, my suggestion as a practitioner is, you have to first doubt why I want 3D printing for this. Is the first question you should start with. Become a devil's advocate. No, first ask why. Cloth means why I want to use 3D printing.
Okay.
It should give you better price. It should make your life better. It should give you better capability, or any one of these. Then only it becomes a disruptive technology. So, just about applying 3D printing to any and everything is not right.
Absolutely.
Okay, so maybe in 3D printing, what you miss in jacquard printing or weaving, what is not possible, that
Okay.
you need to address by 3D printing. Keep
Definitely.
whatever is good as it is. Because 3D printing is not here to replace everything. It is a technology like any other. It is going to complement, the technologies existing today. Okay, but if you find for a particular use, this is the best, you adopt it. So I think this 1 week of program, what Prasad has very well curated and designed, would make you at the end of the week, you'll be in a position to decide, well, I should use it or not. Hope I answered your question.
Yes, sir. Thank you. Thank you very much, sir.
Yeah. Even in the morning session, there was one question that how 3D printing can be used for mass manufacturing. So, see, that is something which we have to evaluate and say what is the specific application. You identify what is the requirement, why you want to use. There are situations where still injection molding may be useful. So that is something which we have to evaluate and decide based on our requirement. Okay,
Absolutely.
so there is one more question in the Q&A part. The question by Manish Jha was asking what skills can be incorporated to students for improving their employment related to
Oh,
additive manufacturing.
very interesting, very important question. As you can see, design itself is undergoing a lot of automation. Okay, manufacturing is also undergoing a lot of automation. So the customization, what you call as mass customization. The morning question what was asked, customization cannot be done by automation or by artificial intelligence. It has to be done by a human being at the back end. Okay, so customization is a one of the very important areas which customization of what you may ask. Customization, mass customization is less related to mass. It is like personalization or individualization. You know, how can I make for example, I want to wear a particular type of button. No, because it's me. You know, who is going to ask if I'm 50 plus? I'm not worried about all that. You know, I'm worried about knowing knowledge, going to places, and all that. You know, but this is called the personas of the user. The users who are youths, you know, or a child born today morning, for example, what after when it starts earning will anticipate what will be the aspiration of that. So today, you know, it is like people say, I have arrived, I am unique, I want to stand out in the crowd. You know, for that you require everything custom made. You know, and just about anything. It can be a cloth, it could be a spectacles, it could be a shoe, it could be a button, it could be a door handle, it could be plate, it could be a food, it could be a drugs. Drugs means, I mean, good for health, not the drugs. You know, it could be anything. It could be a sweet, it could be anything, you know, or the glass what you want to use, a tumbler, you want to have your own, you know, it could be just having your carrying your name. It could be a different shape you wanted, you know, because it reflects you. Then you can just imagine you have furniture, you have car, you have bags, and your watches, your jewelry, whatnot. The whole world. You have toys, and so the whole world will be looking for that, and technology will enable it. You know, they just use a browser, they get in, and they will start designing it, because that's called democratization of design. That means you are going to have a parametric model in front of people can actually pull the design like a rubber band, you know, stretch, pull, push, make it, size it. For example, you want to size to your size, tailor made. You have to just say, input all this, you know. So that's what is going to happen. That means a lot of computing, the back end things that are going to be important. Okay, the content creation, 3D content creation is important. So lot of resources required in the content creation, the file fixing, and people who handle the hardware, the so-called 3D printer. Then people who are not so much educated, but they are into kind of ITI training, they can go for finishing. It could be painting, it could be cladding, it could be, you know, assembly, or it could be fitting in some areas. It could be all that, you know. Those things will never go away. You know, somebody at the end package it, you know, and give it to somebody delivers you to your home. You know, all that things will remain same. So that in future, people should focus on the automation side of manufacturing, automation side of the design. The AI is going to come and kind of think for you. You are going to fight with AI. You know, correct? No. So what AI cannot do, we have to do. What it cannot do is it can think like a common sense and all will be there. But if you want to use super sense of selecting what AI has selected and given, those curative work will be done by designers. You know, so we are actually getting into a uncertain world. You know, and the only way to cope up with the uncertain world is to anticipate, right? That is the only way. There is no insurance possible, no policy possible. You know, only insurance could be prepared, expected, the unexpected. You know, future cast. you know, and don't wait for the change. You create the change yourself. You be the change. I think these are some inputs. I don't know whether I could answer your question or not. And so these are some new areas, for example, if people need to learn IIoT, they have to learn IIoT. Mission to mission learning, the digital twin, the simulation of digital twin, right? And in future, the the components will be built with embedded transducers inside. Correct, no? Because we have a layer control. At every layer, we can control it. The properties can be controlled. So at one layer, I'll say conductive layer. So that is going to create, if a conductive layer is stretched, it becomes, the resistivity will change, or the capacitance will change, or it can become a RFID antenna, all that. So there will be embedded piece, things and transducers inside. So digital twin will be, enabled by these, which are again a product of 3D printing. Okay. So who will do it? Who will design it? Like in molding and all, you're going to have a complex, what is called as conformal cooling. So conformal cooling design and all. People study a lot of heat and mass transfer. I think they quickly finish it and come to conformal cooling channels. The simulation of that, how to optimize it. Those things will really become more and more needed for the industry. So hope I have answered your question.
Yeah, see, that is also some of the things which we'll be discussing in the coming sessions. But just one last question. Actually, there are two questions which are more or less related. So with that, we'll close the session. So I'll just read out the question. One is, can we use metallic or ceramic powder along with PLA materials to enhance the strength of 3D printed models? This is one question. The other question
Along with
is,
PLA, along with PLA.
along with PLA.
Okay.
The other question is somewhat similar. Is there any restriction on material selection for additive manufacturing? Means material which cannot be used with this technology.
Well, today, with the advent of technology and more research going on in the material field, I don't say there are every material available in the world can be used. No, real world has all the material what you see that can be processed by various other technologies. 3D printing, depending on what process, it is a set of technologies. Tomorrow we are going to learn more, deep diving into technology. But you see, some are liquid, some are solid. Solid also like filament, some are like sheets, some are like powder. All these materials are there. Uh, I cannot say, supposing something is photo curable resin, the material what you find, it should also be, um, findable or producible by using that technology. For example, SLA requires laser, and photopolymer is required to bind. And so the technology itself is different. The mechanism is different. So in a way, for every material you may find, you need to find a matching or complaint technology of 3D printing, to handle it. Number one. So today, in a way, it is polarized. You have liquid, you have powder, you have metal, each one having their own challenges to build. That's one. The material, cost of material, which is going into this. For example, in the scrap value of iron and all, it's so low. Kappad wala jo lete, for so many kilos per. But if you come to the metal 3D printing, for example, the raw material preparation itself is so costly. I hope today, tomorrow, you will be hearing about powder preparation and all that. You will understand they are very expensive. Because of the expense, also people are not ready to do everything, but they are very selective. Whichever is moving, only they do. For example, if you want a particular food in a particular fast food joint, they are not given because the traditional food is not available. What is easily producible, like molding idli is available, but if you want to elaborate one, it will take more time. It will be prepared only on a special occasion, like a feast. That way, material also, I think people are very choosy. That drives, the demand for a particular material drives the development also. But I'm happy to say today, uh, there are more than 600 different types of material available for us to build. Okay, and for what at Imagine, we try to match the application area. We understand the context and advise client to use a particular technology. And sometimes we also have told, it's not possible for the use you are looking for. Sorry, there is no material available, no process available. Such things are available even today. I think it will continue like this because as and when the adoption increases, more and more demand for new material will come, and that will drive production also. Because demand drives the production at the end of the day. And if there is no demand, there is no supply. And so that will continue. And you were asking one more question. Um, Today, glass is possible, diamonds are possible, precious metal is possible, many material is possible. Somebody said if we can mix all this, with PLA, yes, that is also possible. Tomorrow we'll try to address that also. It is possible to mix many. We have ceramic and metal. Aluminite is there, which is a combination of ceramic and aluminum. You know, but it behaves more like a ceramic than a metal. Some properties are going to change, and you have many binder jet metal thing processes where it is like a FDM you're going to print, and then you do the debinding, then you do the sintering and get a metal part. So there you have a polymer which is part of it. PLA also, one can mix some metal powder with the PLA and extrude it and then use it. So, for example, you have wood fill, metal fill, clay fill kind of FDM available today. Maybe I'll try to address it tomorrow, but we cannot address all of that. There's it's a whole lot of subject. It can go on and on. I can take a entire week to speak about something. So it's deep down, deep dive. So tomorrow we'll address some of that technology and try to take you through a deep diving more. And hope I have answered your questions. It is possible to make any material. So that's called as material design. Right now, we are in the pursuit of some research, which is to produce biocompatible resins, bioabsorbables, and that's one area. The other area is can I have a kind of a monitoring of insight to monitoring of my build, so that I know the progress of the build. So it's a part of the Industry 4.0, element of Industry 4.0, I can say. It can also fuel some inputs to digital twin, because it is going to monitor the process, right? And so we are working on those. Material composition, that is going to be the future. Okay. Two areas I say. Hardware will all become saturated at some point of time. There will be incremental changes. There won't be anything like SLA kind of thing will come in future. But they will become speed up, they will become faster, cheaper and all that. That's the phase where it's going. But on the materials front and on the usability front, software and all, how can a child touch and make the things possible? That's where more and more of automation or de-skilling that is going to happen. So that will be on the software side. So these are the big areas where we can expect a lot of growth and research also. and faculties can. We can always discuss anytime. We'll be happy to collaborate with you all. To produce, because industry academia interface can do a lot of wonder. What happened in Silicon Valley long time ago, it is happening in India today with startup and whatever. A lot of funding or government funding is also there, like big grant or Didi Prayas, so many things. We'll be happy to collaborate. Okay. Hope I've answered your question, sir.
Yeah, thanks, Dr. Guru Prasad. It was really every time you present, there is definitely something new to learn. So that has been my personal experience. But yeah, it's quite informative, and also see, it's not that you have to give complete details of that. These pointers are very much essential for them to probe in future, and they can take up depending on their interest, and then continue that. So we will be again having you on the workshop tomorrow. So, and if there are any few more questions, and then we can discuss later. So, though we are slightly overshooting the time, I am taking the liberty, hoping that everybody will get their food in time. So, most of them are at home, or maybe where they're convenient. It's not like we have to go to some place to have food and all when we were on campus. So yeah, that is one reason, and this is also a good opportunity for them to interact and ask questions. Okay, so I think with this we thank you, Dr. Guru Prasad, for your
My
wonderful
pleasure.
session, and hope to
My
see you
pleasure.
tomorrow. And
Sure.
yeah, so I think
Thank you.
we will
Thank you.
thank you very much. So we'll break for lunch now. So, and our next session is scheduled at 2 p.m. And hopefully by that time everyone will be able to have their lunch, have some relax for some time, and then come back for the next session. Next session will be by Professor Surya Kumar, who is again a faculty here at IIT Hyderabad. And yeah, we will be joining back at 2 p.m. So in the meantime, if you have any questions, any query, you can post it in the chat box. So and then we will try to address that. Otherwise, we will be joining back at 2 p.m. sharp. So try to join right at the beginning of the session, so that you have enough continuity of that. Okay. So anything the participants want to ask, clarify, or any issues related to the running of the workshop, anything you would like to suggest as of now? Okay. Okay, so fine then. So in case if you have any suggestions, you please put it in the chat box. Yes, we will be sharing the presentations, because some presenters or the speakers have mentioned that they don't like to share the presentation, except those few presentations. I'll collect all the presentations and then share it with you. Uh, and maybe by end of the workshop, we will be having that. Okay. And parallelly, these sessions will also be getting recorded, and I'm not sure whether the live stream will also be available after that on our YouTube channel, which I will share maybe by today last session. And you can watch these sessions live through our YouTube channel. If not today's session, at least starting from tomorrow's session, you will be able to do that. Yes, study material will also be given to you depending on what the presenters shares with us, and then we will also be curating some content so that it will be useful for you. Okay. Yes, somebody was asking like how, see, the whole idea here is to take this to the next level, which is your students, where you are teaching to your students, and then percolate the whatever the knowledge or what you have learned through these, of course these 7 8 days is not enough for us to deliver completely some of the things which many of these experts um, to to completely transform or translate their understanding about the technology and the processes, etc. But I'm sure some of the pointers definitely will be able to help you to pick it up and then take your interest into the account and then develop based on that, and then see how that can be translated in the form of some content which can be given to the students which you are going to train. Okay. So yeah, all suggestions are welcome. We will definitely try to work out based on that, and then we will see how best we can do. We are also trying out some new things this time, and let us see. I am also um, see, this is something which is new, which we have not done earlier. So I'll need your feedback on those things, and then see how best we can customize these things. Okay. So thank you. We will again join back. So it's less than half an hour now. So I think you should get some time to have lunch, and then we will come back at 2 p.m. Okay. Okay. So I will just stop here, and then uh, we will come back at 2 p.m. Okay. Thank you. ಅಲ್ಲ ನಾನು ಈಗ ಅಡ್ಮಿಟ್ ಮಾಡಿ ಮಾತಾಡ್ಬೇಕಿತ್ತು, ನಾನು ಹೇಳಕ್ ಬಂದಿ ನಾನು ಇಂಗ್ಲಿಷ್ ಮಾತಾಡಲೆ ಅವ್ರ ಜೊತೆ ಮಾತಾಡಲೆ ಈ ಬಾಯಿಗೆ ನಿಂತೋಗಿದ್ವಿ ಒಟ್ಟ ನಿಮ್ಗೆ ಏನು ಓದೋದು ಈಗ ಏನ್ ಮಾಡಿಲ್ಲ ಸಬ್ಸ್ಕ್ರಿಪ್ಷನ್ ನೀನು ಊರಿಗೆ ನಾನು ನೋಡ್ತೀನಿ, ನೀನು ಏನು ಮಾಡ್ಬೇಡ. ಹಾ ಏನಂದ್ರೆ Vijay, अभी हाँ now it's streaming but that link we have not shared with anyone. Okay. Uh, अभी now whatever this IIT we were using, no. So with that I am just streaming. I have shared the link. So if that other email ID which you had done. Now anyway it is streaming live on our IIT, but I thought if that is there, we can have that and put the YouTube link somewhere. Yeah. Yeah. So at least you let me know whenever it is active, then we can do it. And उसका credentials वो email हाँ design 1 2 3 4 okay. 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 See now waitlist को भी वेट भेजा है सिलेक्ट हर waitlist है selected को भी probably selected करके वेट भेजा है and now with our rationale is sending calculator. Okay, so I think he has already sent some 20. So right now I am also updating on the website saying that information mail सबसे ऊंचा Same you are become passive onlookers. More ಇಲ್ಲ ಎಲ್ಲಿ ಏನ್ ಮಾಡಿದ್ರೆ ಎಲ್ಲ ಬಂದಿದೆ ಮಾಡ್ತಿದ್ದೆ ಇವೆಲ್ಲ ಯಾಕಂತ passive onlooker ಯಾಕಂತ ಮತ್ತೆ ನಾನು ಮಾಡಿದ್ರೆ ನಿಂಗೆ ಗಂಟರಂಗಿಲ್ಲ ಹೇಳೋ ಗಪ್ಪ ಗಪ್ಪ ನಾನು ಗಪ್ಪ ಅಂತ
ನನಗೀಗ ಬೈಬಾರ್ದು, ನೀನ್ ನೋಡಿಲ್ಲ. ನಾನು ತಗೊಳಿದ್ದೆ ಅಂತ ಅವಾಗ ಹೇಳಿದ್ದೆ, ನೀನ್ ಕೇಳಿಸಿಲ್ಲ. ನಂದೇನು ತಪ್ಪು? ಹಾ, ನನಗೆ ಅನಿಸ್ತದೆ ಯಾಕಂದ್ರೆ ನೀನ್ ಭಾಳ ದೂರ ಬದ್ರಂಗಿಲ್ಲ, ಅದಕ್ಕೆ ನನಗೆ ಕೇಳಿಸಿಲ್ಲ. ನೀ ಹಾಗೆ ಅಮ್ಮ ನಾಳೆ ನೆಕ್ಸ್ಟ್ ಟೈಮ್ ಯಾವಾಗ ಅಂಗಡಿಯಿಂದ ಏನಾದ್ರು ತರಿಸಿದ್ರೆ ಪನ್ನೀರ್ ತರಿಸ್ತಾ ಇವತ್ತು ಅವಾಗ ಪನ್ನೀರ್ ತಿಂತಿದ್ದೆ
Hi, good afternoon. Good afternoon, Professor Surya.
Hi, good afternoon.
Yeah. So we are just waiting for candidates to join.
Sure.
So
I'm here, so
yeah,
whenever you're ready.
yeah. Just wait for 1 or 2 minutes, and then we'll start. Okay, so let us start. People started joining. Yeah, so good afternoon. Welcome, Professor Surya, and uh, welcome to all the participants. So we will be starting the third session of today's workshop. So this third session is handled by Professor Surya Kumar, who is a faculty professor at Mechanical and Aerospace Engineering Department at IIT Hyderabad. So, as morning Professor Venkat Reddy was also mentioning that some of the aspects, the detailed aspects of 3D printing and additive manufacturing, specifically in metals and things like that, will be handled by Professor Surya. So we will be starting with a brief introduction of the speaker, and then it will be over to Professor Surya. Before that, I request Mr. Kamal, who is a student volunteer, to introduce the speaker. And yeah, over to you, Kamal.
Yeah, okay. So good afternoon, everyone. Now, it's my great honor and pleasure to introduce one of the well-known person in Additive Manufacturing Academia, that is Professor S. Surya Kumar. Professor Surya sir is presently working as professor in Department of Mechanical and Aerospace Engineering, IIT Hyderabad. He is also faculty in charge for incubation, innovation, and startup. He has done both bachelor's and master's from IIT Madras and obtained his PhD from IIT Bombay. His current research focus is on large area additive manufacturing, functionally graded materials to twin wire deposition, wired powder hybrid direct energy deposition, variable access deposition, integrated metal additive and formative manufacturing system, thermal balancing approaches for residual stress and distortion control, microstructure evaluation along build direction, post-processing of metal AM parts designed for additive manufacturing. He is also coordinator for a new course launched in IIT Hyderabad, that is MTech in additive manufacturing. Professor Surya has 5 patents and he is also ordered over 30 journal papers and 1 book chapter. So now I request Professor Surya sir to start his talk.
So before I go, can please confirm whether my video, my screen, and my voice is
Yes,
clear?
sir.
Okay,
Yes,
wonderful.
Yes,
Okay,
sir.
great. So thank you, Kamal, and thank you, Dr. Onkar, for a warm welcome. Okay, so I think it's just internal IIT Hyderabad, so feel uncomfortable about the speaker introduction, but thanks for a warm welcome. Okay, so I think so today we'll be talking on 3D printing or additive manufacturing. Uh, so what I will do is in this session, I'll give you a brief overview of all the areas and all the subjects which are there in additive manufacturing, so that you can look at all of them in perspective. And then tomorrow I think tomorrow also I'm having a session at 9:30 something. Okay. So in tomorrow's session, I will be going in deeper into the metal processes and what is the vis-a-vis comparison, where do the metal processes, which process is good for which material, which process is good for what material, etc., kind of details we'll going through. Okay. So today's talk, the intention is to give a more broader overview of the different various AM processes where they stand. Okay, so I think anyway, this is my standard slide, so I think I will just skip it. Okay, so I think additive manufacturing or 3D printing. Okay, all of us have heard about it. Okay, but why is it so popular? Okay, so so there are, if you look at any fabrication technology, okay, so there is forging, there is welding, there is casting, there is machining, okay. Why is it that among all these, additive manufacturing stands out, okay, and what makes it so sought after, so popular, and what exactly differentiates it from other AM process, other manufacturing processes or other mechanical processes, etc. Okay, so that I think is a crucial question. Okay, why is it so popular? Okay, if MEMS, if NEMS, if casting, etc., not equally popular, why is AM so? Okay, so I think one of the, there are many reasons, but if you look at it traditional manufacturing or fabrication is categorized in the form of casting, forging, welding. You have machining, you have in machining, you use a lathe, you are using a milling, etc. etc. Okay, I don't need to elaborate this. Okay, I'm fairly confident that most of the attendees have some background about it. Okay, but the point here is any process, any fabrication you need to do. Okay, it presumes that you know all this and you know which is good for what system or what method. Okay, so for example, if you want to do a cylindrical machining or axisymmetric machining, you know, or I mean, it is expected that the user knows, okay, axisymmetric means lathe is good, geometry. Or if orthogonal profiles, milling is a good method to do it. Okay, so that any fabrication, traditional fabrication methods presume that the user has done or has a good amount of familiarity with all the processes, casting, machining, lathe, shaping, etc., etc., and knows how and what to do, which to select, etc. Okay. Whereas in the additive manufacturing, the whole idea is how can you shorten this learning curve. Okay, so I mean, there is a fair amount of learning curve involved here. So one has to go through all this process. Okay. So the traditional manufacturing requires user to be familiar with lot of processes and competent enough to select the right process. Okay. Now the question here for us is, can fabrication be done by a person with no fabrication background? Okay. So that's kind of the idea here. Okay. So that is where the additive manufacturing comes. I think before I go into why and how of it, okay. But I mean, just to conclude this point, okay. So the bigger thing about additive manufacturing is, in a way, I mean, in a jovial manner, additive manufacturing is a fabrication even meant for them. Okay. So you don't have to know any fabrication methodology. It is a methodology where even a school kid, I mean, let us say a 10th class or 8th class kid also can use and create components, fabricate components. Okay. So that's the great thing about additive manufacturing is it does not presume you have a lot of fabrication knowledge. Okay. Does not matter what is your background, whether you were even in a, I mean, school or not even a mechanical engineer, you are from, I mean, maybe even an arts guy. Okay. Still, this is a methodology which you can use. Okay, that's what makes it popular. Is it's a manufacturing technique which can be and is being used by everyone across the board. Okay. So before I go into how it does it, what are the things, etc. Okay, so let's kind of look at what it can do. Okay, so these are all the things which are possible today. We have 3D printing for designs, we have 3D printing for jewelry, we have 3D printing for electronics, you even have 3D printing for fashion also. Okay, so for example, I mean, this is a nice model of a shoe. Heeled shoe. Okay, so as if somebody is bearing the weight of it. Okay, so you can create all such kind of designs, etc. Then you can have today 3D printed artificial skin is already a reality. People are looking at 3D printed kidneys and 3D printed tissues, etc. in the near future. Okay, I think again Dr. Palguni and Dr. Subha will be talking about it. Okay. And you have even I mean, in fashion there is even a dedicated fashion show about 3D printed apparel. Okay, so that's kind of the things how 3D printed. Okay, so all the dresses are 3D printed. Okay, so that's kind of again even in fashion accessories, etc. how it is done. And of course, you have it in dental, you have it in toys, you have it in chocolates also. Today, 3D printing chocolates are available. Okay, so where you can create complicated. I think you might have come across this news headline where they have 3D printed a pizza inside a space station and ate it. Okay, so all these are kind of irreality today. Okay, so I think that's kind of how all this are happening. Okay, now. But again, I mean, and there is a lot of hype around it. Okay, so we call it third industrial revolution. I mean, this thing, etc. Okay, and I mean, as a researcher in 3D printing, I think that is the correct word. Is hype. Okay, it's not real. Okay, 3D printing is a good technology, but it is not a magic solution for all the problems of manufacturing. Okay, I mean, so that you must always keep in mind. You must always keep it as a good methodology, a good, I mean, a fairly good methodology, a fairly good process. Okay, but it's not a magic solution. It's not one solution for every industrial problem. Casting is still going to be there, forging is still going to be there, CNCs and robots are still going to be there. Okay, this is not intended to replace any of them, these are intended to augment them only. Okay, and I mean, people who say that are more salesmen than real researchers. Okay, so real researchers always take what the 3D printing shows. Okay, so I mean, I think that's again you have to keep in mind. Okay, keep a balanced view. Don't go gaga over 3D printing. Okay, I mean it's a good methodology, but it's not like top Mario type. Okay, so I think that's kind of the background. Okay, now let's come into how it happens. Okay, I think what it can do we have seen. Okay, now how does this happen? How does 3D printing shorten the learning curve? Okay, reduce the ease with which a person can use it. Okay, how it does is very similar to how your Lego concepts are there. Okay, so the idea is, I mean, so with a simple Lego kit, you can construct a castle, you can construct a house, you can construct some cycle. I mean, different things you can construct. Okay, but it is the same entity which is being taken up in different patterns. Okay, the same is the concept along associated with 3D printing. Okay, so the idea here is don't look at the shape. Okay, but look at any object as a sum total of repetitive elements. Okay, so what do you mean by that is everything is a repetitive element. Okay, so what is the pattern which it is repeating? Okay, so that you concentrate. Okay, let me give some examples to elaborate this concept. Okay. So, for example, I mean, so let us say this is a hollow cylinder. Okay, now you are just what you are doing here is stacking up coins, okay, in a particular fashion to create a hollow cylinder, and the same coins you may stack up in a different pattern to probably create a pyramid or some cube, okay, in a different set of geometries. Okay. So, if you want to understand the 3D printing, I think the best corollary is 2D printing. If you look at historically, earlier all the 2D printing was associated with blocks. Okay, so there was a printing press, there was a block, okay, or there was a typeset. Okay, and as long as this was the methodology, there used to be always a very limitation in how you were doing it. Okay, so I think I mean we must have come across the concept of blocks and offset blocks, okay, and typesets, etc. Okay. Components is looked as a you are looking at it as a particular alphabet. Okay, every alphabet needs to be replicated. Okay, we need to have a one size for capital, one size for small, one size for Times New Roman, one size for Verdana. Okay, one size for Arabic, one size for English, etc. etc. Okay, so that's the problem. Okay, it's very similar to how we are facing in the manufacturing techniques, where one shape it is milling, one shape it is shaping, one shape it is lathe, etc. Okay, what has happened is how the 2D printing evolution has happened is you stop looking at the shape, but as a sum total of dots. Okay, you don't care whether it is a A, you don't care whether it is a D, whether it is English, whether it is French. Okay, at a given point, is there a dot or is there no dots? Okay, the moment you are able to visualize and look at the same geometry in a different perspective, okay, that is how the 2D printing revolution was possible. Okay, now I have a single 2D printer which can print large size, small size, French, German, I mean Times, Word, and everything I can print using the same printer. Okay, and how was this possible? By essentially stop looking at the alphabets as alphabets, but as a sum total of repetitive elements. Okay, that's the core of 3D printing. Okay, so here also what we are doing in the 3D additive manufacturing is taking any complex shape. Okay, we don't care whether it is a cylinder, whether it is axisymmetric, whether it is rectangular, whether it is a torus shape. We don't care. Okay, what we do is break it into number of layers or number of slices. Okay. In this manner, any geometry, any complex geometry can be etched. Okay. So this is how the 3D printing revolution was made possible. First is the conceptual breakthrough. Okay. Then comes the implementations, etc. Okay. But the first point is what is the concept you are using to create multiple components using the same mesh. Okay, so this is what 3D printing does. Okay, so you kind of take a CAD model, reduce it to multiple 2D layers, and then realize each 2D layer in a given manner. Okay, so kind of there are different methods for doing it. Okay, so we will go through that. But the idea still slicing remains the same. So, for example, I mean, again, you can visualize it in some something like this. Okay. So, where I mean, so it's the same rope which gives you a basket, which gives you a cup, which gives you I mean, a bigger fruit basket, everything. Okay. So, it's essentially a pattern. Okay. The same pattern, by creating it in multiple fashions, you generate multiple objects or geometries. Okay. So that's the concept. Okay. I think I mean this is our favorite picture. Okay. I am sure Professor Reddy might have also shown in the morning. Okay. But I mean kind of the whole idea of this is very similar to you recollect the situation where Hanuman goes to Lanka and then I mean he's not offered a seat by the Ravana and he makes his own tail. Okay. To create a chair. Okay. So that is our very similar. Okay. So the same tail can be used to create a chair, that can be used to create a wall, can be used to create a this thing, etc. Okay. The entity is same, the pattern is different. Okay. And by controlling the pattern, you create different geometries. Okay. So that's the core idea of 3D printing. Okay. So I think I mean, and it's not a novelty. Okay. So the novelty is in how you are able to achieve it. How you are able to use the materials available, how you are able to achieve the heaters and the controllers, etc. available to achieve it. Okay, that's the kind of idea. So this is, I mean, I think something how it looks like. Okay. Okay, you can see the nozzle is extruding the material and pressing it in the required space. So if somebody is familiar, can anyone guess what is the shape being made? No, Star Wars stands here. Okay, so the master Yoda. Okay. So what is done here is if you look at it, okay, it's just material is coming, being extruded and deposited wherever it is required. Okay, that's it. Okay, and this simple concept you can use to create various geometries, various objects, etc. Okay. This is a beautiful time-lapse image. I mean, it's not so fast. That's what I mean. It takes a lot of time. Okay, but it illustrates the concept of how you can slice. Okay. Okay. In the end, it's a complicated geometry. Okay, I mean it's quite a fractal geometry, pyramid of pyramid into the pyramid, etc. Okay, so I mean this is a very good fractal geometry. Okay, and a quite complex one. I don't think there is any manufacturing method which you can manufacture this directly. Okay, but what you have done is you don't really care how complex the geometry is. You just care one layer at a time. In that layer, what is the XY positions and movements you have to fill. Okay, so all you care here is in the 10th layer or some 50th layer. You just need to fill 16 squares or 20. I mean, I think here 4 into 4. Yeah. Okay, around 16 squares here. Okay, so that's all. Okay, how to fill 16 square is what you care. Okay, then again next layer. Okay, then again, okay, so probably again another geometry, another shape. Okay, so a complex problem is broken into multiple small problems, small single layer challenges. Okay, again, I think this video is beautiful. You can go on watching it for a long time. Okay, you can see how the shape is slowly evolving layer by layer. Okay, look at the complexity of this geometry. And I think, I mean, if you are given this geometry directly, okay, and asked to fabricate it, it's fairly complex. Okay, I mean, it's fairly complex, and I mean, not an easy job to make it. But what we have done here is not the 3D layer, just the 2D layer. Okay, maybe 100 2D layers, does not matter. Okay, at a given time, we are just solving one 2D problem. Okay, so if you look at it, okay, it's one circle here, another circle here, another circle here, another circle here. That's all. Okay, and because you are able to do it in a coding fashion, you don't even worry about the repeatability of it. Okay, you can, I mean, run the same code for 1,000 times. Okay, and get the results. So this is what makes the 3D printing so easy in its approach. Okay, I think again different geometries. You see the clock behind. Okay, it takes a long time. It's not. I mean, the video is a very accelerated video. It does take quite some hours to build these parts. This is also not just about printing. This is a very good example of design for 3D printing. Okay, I think, I mean, I'm sure there is one session about that topic. Okay, where you design the component such that it is easy to 3D print. Okay, you'll see how that is done. Okay, so if you look at this geometry, it is very complicated. If you directly go for the print, so it's not. It needs a lot of support material. There are a lot of loose ends. There are a lot of weak links, etc. Here. Okay, so the same component you have done it in a different fashion. I mean, I think in the concept of design for 3D printing concepts, etc. Okay, so there is a lot to, you can also improvise how you do it. Okay, okay. For example, you can create a gun, you can create a wall, you can create spaces. I think this is Gandalf, if I remember correctly. I don't recall. Again,
Oh, ಸಿಕ್ಕೊಂಡು
okay, again, look at the complexity of this geometry. I don't think except for 3D printing you can create this by any other means. But 3D printing makes it so easy. Okay, I mean, I think you feel like, oh, it's so easy a geometry. Okay, I mean, this is the idea. Okay, and I mean, I think, let me just okay, I think, I mean, this is kind of how it does, etc. Okay, so now there are many variants of 3D printing. Okay, so binder jetting, direct energy deposition, laser, fuse deposition. I'm sure you will cover all of them in the coming week. Okay, so what is common among all of them is you are slicing them at a given point. Okay, so all this, no matter what is the this thing, you are going to slice them and you are going to make one layer at a given time. Okay, so that's why it's also sometimes referred as layered manufacturing also. Okay, so solid silicon fabrication, layered manufacturing are also other means for referring to additive manufacturing. So one common thing which is, sort of essential across all the variants is you're realizing you're dividing the component into layers and you're realizing each layer at a given time. Okay, so that's the idea. There are many differences. Okay, you may use sheet, or you may use liquid, you may use wire, you may use powder as the raw material, you may use laser, you may use glue, you may use a electron beam, you may use arc. Okay, again, 100 different variations in how you do the layer. Okay, but that the layer is made is common across all of them. So that's kind of a crucial important. So now these are all, there are, according to the ASTM standards, there are currently 7 additive manufacturing techniques which are kind of categorized. 7 techniques. Okay. So sheet lamination, material extrusion, wet polymerization, powder bed fusion, binder jetting, material jetting, and direct energy deposition. Okay. So in this session, what I will do is I'll give you a brief overview of each of these processes. And in tomorrow's session, I will pick from among these the metal ones and go into the more detail of the metals. Okay, so that's kind of the plan for today and tomorrow. Okay, so let's go into one by one. So the sheet lamination. Okay, so the sheet lamination, what happens is the concept is nothing but you are creating a layer. Okay, how do you create a layer? Okay, a single layer. Okay, so the easiest one is your paper. Okay, so for example, I'm sure you have seen that Shawshank Redemption, or there are many movies, I believe. Okay, or even I think Savarkar is believed to have hidden in the same fashion, etc. Okay, so this is a 3D geometry. Okay, so this is a 3D geometry. Okay, but if you look at it, it's just sum total of maybe 500 pages, 500 single 2D geometries cut into a profile of a gun. Okay, one cut, second page cut, third page cut, fourth page cut. You do it 100 times, does not matter. Okay, but end of it, it is one page and one page into a profile which is a 2D profile, not a 3D profile. So that's the basic idea of your process here. Okay. So this is the same method, the concept which is used in the sheet lamination. The first of that is what is called as laminated object manufacturing, okay, or LOM. So what it does is it takes a roll of paper, okay, and then cuts the geometry, periphery, etc., outer periphery with the help of a laser, okay, and then stacks it up. The next layer comes down. Okay, again you do the next part and next layer in that fashion you go on build. Okay, so let me just show the video of this process. Okay, so this is your process. So what you have is you start with a paper layer. Then you see the laser cutting the paper. Then you see the paper rolls, next layer of paper comes, and again you have this roller which is gluing it to the previous layer. Okay. And again the next layer is cut like that. Okay, so if the process repeats, goes on and on. Okay, so what it does is once the layer is created, the platform moves down, then the next layer comes in the place. Okay, it goes on and on. And then finally what you have is the build, which is nothing but lots of layers of paper stacked one over another. Okay, and you remove all the unnecessary parts out from it. Okay, and you are left with the final component you want. Okay, so this is nothing but sequence of paper layers 2D cut in a particular 2D platform, stacked and joined together. This is kind of how the actual process looks. That's the animation. This is the actual process. Okay, you can see the laser moving on the paper and burning and cutting the paper in place. This is how the process kind of feels like, looks like, etc. Okay, so it can create pretty much large components also. Okay, and typically many of the times it has a little brownish tinge, although you are using paper, because you are burning the paper in a way. Okay, so you kind of have a little brown finish to it. Okay, so these are some components you can see being manufactured using the LAM process. Okay, so again, I think this is another component which is manufactured through LAM process. Can anyone guess what is special about this component? Any guesses? Okay, so I think so this is a assembly which is not assembled. Okay, so typically the word assembly means there are two components, you are assembling those components together. Okay, that's the word comes from assembly. Okay, now here is the assembly which is manufactured as it is. Okay, it is a assembly which is not assembled. Okay, so kind of contradiction of terms there, but that's where AIM comes in place, where such unique features and shapes can be easily manufactured right away. Okay, then let's go to the next process, what is called as material extrusion. Okay, so here what is happening here is you have the wire in the form of a extruded molten plastic, which is coming through a nozzle. Okay, falling on the nozzle, and then from the nozzle falling onto the previous layer. Okay, in the molten form, and then getting heated and getting joined with the previous layer, retaining the shape. Okay, I think let me. Okay, so this is how it looks like. Okay, so you have the raw material in a spool form. Okay, it is being pushed into a chamber which is hot condition. Okay, so it melts there. Then it comes out of the nozzle into the molten form. Okay, forms or falls on the previous layer in the molten form. Okay, but because it is in molten form, it gels with the previous layer, bonds with the previous layer, etc., etc. It happens. Okay, and then shape is created. Okay, so this is, I think, process how it looks like. So this is your nozzle, and the molten plastic is extruded through the nozzle. So the plastic comes out in the molten form and then solidifies. Again, next layer like that. My earlier teacher used to give the example that it's almost like jalebi making. Okay, you squeeze, so what happens in a jalebi is you squeeze it out of a nozzle, it falls in the fluid form into the oil, and then solidifies and retains the shape. Okay, so this is very kind of similar in nature. So that's how you can use this process. Okay, what is called as fused deposition modeling or FDM. Okay, so it's also this umbrella of technologies is referred as extrusion process, because you are extruding the material from a nozzle. Okay, that's the reason why these are processes are referred as extrusion based processes. Okay, this is again another. Again, this is the physical version of the process. And this is how it looks like in the reality. Okay, so how the machine looks like. You can see that this is the wire spool. Okay, and the wire is being pushed from this nozzle, white color nozzle here. Okay, and then falling onto the base plate in the liquid form, fluid form, and then cylinder. Yeah, you can see this here. How the material is being added there. So different shapes, different geometries, etc. can be created. So this is the basic idea of FDM process. Okay. Now FDM process is generally the most popular and the most common among all the 3D printing processes. Okay. So if somebody does not say just said 3D printer, but did not mention which method or which geometry, etc. Okay. I think by default you can always assume that it is this FDM process. Okay. So that's kind of how popular it is and how versatile it is. It's also one of the processes which is in a way the cheapest also. Okay, I think 3D printer can come under 30,000-40,000 also today. Okay, the kind of simple 3D printers we are looking at today. Okay, so this is the most popular, the most variant, and the most, affordable also in a way among all the 3D printers technologies. Okay, so unless otherwise specified, if just somebody said this 3D printing, you can default assume it to be extrusion based FDM process. Okay, so now let us look at a geometry. Okay, now let us look at this kind of a geometry. Okay, so it's all fine. Okay, so till this layer it is fine. Okay, what happens is when you are looking at this layer, when you are making this layer, where does this happen? Where does this material, green material go? Okay, so imagine it like very much like our building of walls. Okay, so you can put one brick or another brick. Okay, so building a wall is not a difficulty. Okay, you have the base, you put one brick or another brick, etc. Okay, but when it comes to the roof, you don't have that luxury. Okay, you can't just put a brick in the air. It will not stay there. It will just fall. Similarly, you can add material comfortably till this point. Okay, so you are adding material on a previous material. Okay, so it will stay in place. But what happens is when you are adding this layer, okay, it does not stay there, it just falls. Okay, so that is how a problem with the FDM process or many other processes also. Okay, how it is tackled is again very similar manner to how we tackle, for example, a house roof. Okay, what do you do for a house roof? Okay, you create temporary scaffolds. Okay, so so you create some dummy wooden things, then you pour the concrete, you remove the scaffolds. Okay, so similarly in 3D printing also. Okay, so for the same reason you use two different materials. Okay, so the white color is the model material, and you see the black color one is actually the support material. Okay, so this support material can be removed after the part is done. Okay, and you will realize that this support mechanism comes in various forms, in various processes and techniques. Okay, in some you use a different support material. In some processes you may use the same support material. Okay, as scaffolds. Okay, in some how you break the support material, what is the maximum overhang you can get, etc., etc. It's always a challenge. Okay, so let's keep one thing in mind. Support mechanism, okay, is again a concept which comes across in different machines, in different forms, in different contexts, etc. Okay, but I think that's always the rule. Wherever there is a overhang, wherever there is a overhanging instance, wherever there is something which is going beyond, which does not have a previous layer, which is tends to fall down. Okay, you need some extra mechanism to handle it. Okay, this is kind of how it is. Okay, so FDM does it beautifully. Okay, so FDM process, particularly statuses, Okay, what it does is it uses a secondary support material. You see here, black color one, and even more beautiful that it is water soluble. Okay, you just put this part in the water ultrasonic tank or something. Okay, then all the unnecessary material just melts away in the water, and you are left with the final plastic component you are interested in. Okay, so that is how they handle the support mechanism charge. Okay, so there are also other variants of this process. Okay, so one of the variants is what is called as contour crafting. Okay, so in contour crafting, what happens is you're just going same concept but mega about it. Okay, you're going 10 times, 20 times bigger in it. Okay, you use a nozzle. So the concept is you use a nozzle, extrude through the nozzle. Okay, now instead of extruding more than plastic, what they're doing is extruding cement in it. Okay, you can see essentially how the cement is being extruded from the nozzle. Okay, to create walls. Okay, you can see giant walls can be also created. Okay, the concept remains the same except that the size is increased, and the material is instead of plastic cement. Okay, so this is one variant of 3D printing. Okay, so I mean, and there are other variants. So, for example, you can also extrude chocolate. You can extrude ceramics. So you can print. I mean, so today 3D printing pottery is also famous. Okay, so you extrude mud ore from a nozzle and create components. Okay, so there are. I mean, so the basic concept is in the extrude earlier method, there is a nozzle. You're extruding material through the nozzle. Okay, that's the basic. Okay, then you have the third method, what is called as back photopolymerization. Okay, here what is happening is you have a technology where the raw material is no longer in the solid form but in a liquid form. Okay, and then this liquid, wherever the laser is passing, okay, that location it is selectively solidified. Okay, so what you are doing is you are taking a photopolymer here. Okay, so this liquid is being selectively converted into a solid photopolymerized to generate into a solid. Okay, so let's kind of look at how the process looks like. Okay, I think the starting processes are about the same. You take the CAD model, you slice it into layers, etc. That's universally true. Okay. So this is your resin pack, let us say. Okay. So where the photopolymer resin is poured. Okay. And what we do then is wherever you want it to convert it into a solid, you trace the laser. Okay, you can see the blue light passing across. Okay, so that's nothing but the laser tracing your geometry. Okay, you kind of do the next layer. And finally, once you remove the part, okay, what happens is here, wherever the laser was moving, that part is converted into a solid, photopolymerized, and the remaining part remains as a liquid. Okay, so the moment you kind of take it up, all the liquid flows away, and whatever is the part you want, that solid part alone remains. Okay. So this is very popular for dental implants or any other accurate geometries, even in the jewelry industry also it is very popular. And subjected to some treatment if you want it to be stronger, etc. etc. Okay, so the basic idea is you are taking a liquid, a vat of liquid. Okay, so that's the reason why it is called as vat polymerization, because you're taking a tank of liquid, okay, a photopolymer liquid, then selectively passing laser. So selectively means you're not passing the laser completely. Wherever you wish it. Okay. So selectively passing the laser where you want the component to be solidified. The remaining part remains in solid liquid, and wherever you are passing it converts into a solid, and that's how you are creating the geometry. Okay. Again, layer by layer, that's fine. Okay, one layer after another layer you need to. Okay. So this is kind of how the process finished parts look like. Okay, the left part. Okay. This is a casted component out of it. Okay, so the left is how the finished SLA process part looks like. Okay, the right is a more of a can say the casted component out of it. Okay, so some of the other geometries, etc. Okay, so some of the other processes, etc. Okay, so it's very common in what you call jewelry industry. Okay, so in jewelry industry, this is used for casting components, patterning components. Okay, so you create the pattern, wax patterns, then that you use as a investment casting pattern for creating gold or silver ornaments. So that's kind of the first three processes. The fourth one, what it does is, what it uses is powder bed fusion. Okay, or where metal powder or powder in general is used as a raw material for creating the components. Okay, so typically what happens is you have a powder tank. Okay, where a thin layer of powder is spread. Okay, then I think. Okay, yeah. Okay. So what happens is a thin layer of powder is spread. Okay, and then again wherever you want it, you selectively sinter the component or fuse the component, melt the component wherever it is. Okay, and that part okay becomes solidified. Okay, so you can see essentially. So this is all loose powder, and wherever the laser is falling, okay, that part alone becomes solid in nature. Okay, so that's kind of how the process looks. Let me show you a video of the process. So you see, there is a thin spread powder, okay, and you can see wherever the laser is moving, sparks moving, that part is solidified and sintered, and you can see the change in the texture there. You go on one next layer like that, okay. And after all the build is done, you can just remove the part. So all the remaining is loose powder which just flows around or cleans around, and then you are left with your final component. Okay, so this component in shape. Okay, so that is how the SLS process works. Okay, so again I think another. So I mean, so the same concept. You can see how the laser is moving across and how it is centering the parts. Again, you see there is a recoater. Okay, so there is a wiper which comes and applies the next layer. Again, the process repeats. So you have a new layer of powder, again which is being sintered. Okay. The process goes on. So this is how the powder is coming back. Okay, you can see the tank is moving down every layer. Okay, and then the wiper is applying a new layer every time. And then you can create the final. Okay, so this is how the process looks like. So you can, so this is one of the first processes which could create metal components also in reality. All the processes till now were predominantly with polymers and plastics, etc. Okay, so this was one of the first processes because you were not just using any other powder, you could use even metal powder. Okay, here's one of the processes. Okay, and that is how you are creating metal components here. Okay, so this is one of the first processes. Of course, you can also create polymer powders, polymers also as powder and create polymer components also. Okay, but metal was also possible, made possible using this technique. Okay, so there are various applications. For example, conformal cooling decks. Okay, so complex channels could be generated. Okay, you can see how the channels are internally facing around. Okay, so such kind of complex geometries. Okay, which are usually not possible for other methods can be made using this. Okay, it is very popular with biomedical implants also. You can create biomedical, kind of human use grade implants, okay, made up of titanium, etc. And we can also create these fine mesh and lattice structures. Okay, you can see the nature of this lattice. Okay, so it has very excellent strength to weight ratios. Okay, where such fine geometries and lattices can be created. These are some of the advantages of our post process, what we call as powder bed fusion. Okay. So now there is a small change. Okay, so the concept remains the same. Okay, somebody thought, okay, you are having a powder, you're spreading the powder, okay, and you are then heating it and melting it. Okay, why heat? Why melt? Instead, why can't you spray a binder across? Okay, not for metals, but for example, if you are handling some other concept. Okay, so the same process, what it does is the spread the layer, spread the powder, but instead of heating it, it sprays a binder. Okay, so that is the next process, what is called a binder jet. Okay, so here what you do here, see here. Okay, so the same. Okay, so you have a powder, you spread the powder. Okay, only difference being you are using a inkjet. Okay, or you're dropping binder droplets onto the process. Okay, and the beauty of it is when you're dropping the binder droplets, you not just need to drop normal, but you can even drop it in multicolor format also. Okay, so you can, when you're essentially spraying glue, right? Okay, so when you're spraying glue, you can not just spray normal glue, but you can spray green color glue, blue color glue, red color glue, and RGB combination, create any color pattern also. Okay, so that's the beauty of this process. Some of the components which you can see. You can see, so the same technique is same. Okay, you are spreading the powder. Okay, and then you are using a spray to selectively bind that powder. I think here they are using starch as the powder. And again, loose powder is taken away, and finally you have the final strong component. Okay, so this is your component. Okay, which is glued together by using a glue, spraying the glue. Okay, and so that is how the component is. Okay, as I said, the beauty of this process is you can use color glue also. Okay, to create multi components. So this process allows you to create multicolor components. In fact, I think, frankly, this is the first, and even today, this is probably the only process which allows for you to create multicolored components in the 3D printing processes. Okay. You can, I mean, kind of, so you're using a blue color glue here, you're using a red color glue here, you're using yellow color glue, I mean, or a mixture of them, etc. Okay, so that's how you can get it. The next one is again borrows from the previous again. Okay, just like the fifth one borrows a little from the fourth, the sixth borrows a little from the fifth. Okay, and what it does is when you are spraying, okay, why spray the binder? Why not the complete material? Okay, so it is essentially kind of very similar to your printer, okay, color printer. If you take a printer, okay, so for example, if you have a paper, okay, and take a print, if you run your paper, you can see a small material being deposited on the surface. Okay, so that's how you are peeling the part. Okay, now imagine instead of using different papers, you're using the same paper again and again and again. Okay, what happens then? It creates layer on another layer, another layer, another layer. And you can build the component by spraying microjets on the component. Okay, so that is the process which is referred as material jetting. Okay, it is the same technology which you use, for example, in your color printer. Okay, in HP or whatever is the color printer you have. Okay, here what is that doing? It is spraying micro particles or micro amount of material. Okay, and that is used to build the complete component. Okay, so this is how the process looks like. Okay, so what you do, you're taking a standard inkjet or a kind of a jetting head. Okay, and you are jetting. This time you are jetting and completely creating and adding the material. Okay, then you have a I mean, UV curing, etc. So that liquid is converted into solid pretty fast. And let me play a video of it. This is all the CAD preparation.
ಗೊತ್ತಿಲ್ಲ ಫೋಟೋ ಮಾಡಿದ್ದು ಏನದು
You can see this is the print head which moves.
ಪ್ರಿಂಟರ್ ಏನದೆಲ್ಲ
Then there is the
3D
ultrasonic
printer
light which then converts the liquid into the solid form.
ಡಾಟ್ ಡಾಟ್ ಕೊಟ್ಟು ಅಷ್ಟೇ ಇದೇನು ಮಾಡ್ತೇನಿಲ್ಲ ಮಾಡ್ಲತ್ತೇನಪ್ಪ ಏನು ಮಾಡೋದಾಗಲ್ಲ ಸುಮ್ ಓಡಾಡ್ಲತ್ತ ಅಷ್ಟೇ
Okay, you can go on.
ಆದ್ಮೇಲೆ ಹಿಂಗ್ ತೆಗಿತಾರೆ.
I mean, you do some cleaning exercise, you want to remove the support material.
ಅಪ್ಪ ಯಾಕೆ ತೊಳಿತಾರ ಅವನ್ನ
Support material deposit.
Okay, so this is a component which is nothing but your spray of liquid
ಒಂದಸಲ
polymer. Okay, layer by layer, 16 micron, 20 micron, small layers you go on and on and on. Okay, and then you create the final component you wish to etch. Okay, so that's how the process works. Now let's come to the last one of them. Okay, what is called as direct energy deposition. Okay, so in the direct energy deposition, typically lens is the most famous of them. Okay, what you are doing here is you are taking a focused thermal source, maybe a laser, maybe a electron beam, maybe a arc, does not matter. Okay, and then you are fusing the particles into it. Okay, so if you look at it, okay, you can see essentially in the center there is a laser falling, and from the sides you see the powder particles are being bombarded and sprayed into the nozzle or into the laser molten pool. Okay, so that is how the part is created. Okay, so this is kind of how the machine looks like. Okay, so you have your machine. Okay, this machine, I think lens machine is available in DMR also, and in fact even in IIT Hyderabad we have a similar variant of it. Okay, so you come with the, okay, so this is your raw material, metal powder. Okay, so you see what is happening is there is a laser beam which is falling in the center, then powder particles are sprayed into that molten pool, and that is how you are creating the layer. Okay, a particular layer is being created. Again, I think, okay, so this is a good example. and other things. Okay, so there are various variants of this process. Okay, but the idea here is there is a thermal energy, there is the energy source, and there is a raw material source. Okay, and then you are fusing them together to achieve a layer. Okay, so that's the basic concept of this process. Okay, that's what kind of how you are depositing it. Okay, so there are various variants of there are many variants of this process. Some use laser, some use electron beam, some use arc, some use wire, some use powder, etc., etc. Okay, so that thing that we will discuss tomorrow. Okay, but this is kind of the body of the process. Okay, so I think that's kind of all the processes which you have come across. Okay, so just okay. So you, in one you use a sheet as the raw material. Okay, in another you are using a nozzle, molten or liquid form, fluid form, which is being extruded from the nozzle. We are extruding it from the nozzle. The second. In the third, you are using a liquid raw material and then photopolymerizing it using a laser. In the fourth, you are using powder as the raw material and heating it, fusing it. In the fifth, you are using again powder, but instead of heating, you are binding it. Okay, using a binder, using a glue. Okay. In the sixth, you are using sort of jetting the material directly. And in the seventh, essentially, you are having direct energy deposition where energy is directly used on the point of contact to create the component which you require. Okay, so these are kind of all the processes available today. Okay, now I mean just a brief some 2-3 slides about what's happening at IIT also. Okay, so I think one of the major I mean initiatives at IIT Hyderabad has been a digital fabrication course, which is a first year common course across all streams. Okay, I think again Dr. Pankar is a champion of this course, and I think he would be able to talk and discuss more about it. Okay, but that's kind of one of the unique things about 3D printing at IIT Hyderabad. Okay, where every student, BTech student who joins IIT Hyderabad, does this as introduced to 3D printing right in the first semester. Okay, so that's the basic idea. Okay, and I mean, so we teach them CAD modeling, we teach them 3D printing, etc., etc. Okay, so kind of the parts they are made, etc. Okay, and some CAD modeling we teach them. Okay, so some 3D. Okay, so some other components, etc. are possible. Okay, so and then we also have a good research team in metal additive manufacturing, particularly. And I mean, a much bigger team, close to 15-20 faculty working in other aspects of 3D printing, etc. also. Okay, so we have fairly good systems. So we have three major metal additive manufacturing systems under a single umbrella. I don't think any other IIT has any other IIT has such systems. All okay. So some may have wire arc, some may have powder bed, some may have lens, etc. Okay, we have all the three, the major three metal AM systems, and in a single umbrella and a single roof side by side. Okay, so I mean, so we do a lot of visual studies, etc. Also, so we have wire art additive manufacturing setup. We have a DD powder bed, powder based DD type, setup. We also have a powder bed fusion system, which is created by GE. Okay, and we have fairly other machines, FDM printers, back polymerization printers, composites, 3D scanners, etc. And I mean, I think one of my particular focus has been to create components in large metallic components. Okay, so large scale metallic object manufacturing is one of my areas. Okay, so I think these are some sample components developed in our lab. Okay, so again, I mean, 5-axis depositions, etc., etc. I've been working. Okay, so. I think that's kind of the whole thing about additive manufacturing, what goes on in the world, then what's the various processes, what's going on in the IIT Hyderabad also. Just about it. Now I think I mean let's just pause for a moment so that we kind of focus and summarize. Okay, I think this summary is important. Okay, so just I mean I just wanted to pause here so that we can summarize what we have learned and what is the key takeaway points today. Okay, yes, I think I'm kind of So now first let me start with some usual questions. Okay. So is 3D printing cheap? Is 3D printing fast? Is 3D printing accurate? Is 3D printing metallurgically good? Etc. etc. There are multiple questions which keep bothering many of us. Okay. So let me try to address them one by one. Okay. So the best way to understand 3D printing is again going back to the 2D printing. Okay. So for example, take a offset printer and a office laser printer. Okay. So the offset printer, the cost of the template, for example, maybe 20,000 or 2,000 rupees. Okay. But the cost of single page is just 5 paisa, 10 paisa. So whereas office printer, I mean sorry, laser office printer, okay, cost 2 rupees per page. Okay. But there is no additional cost. Okay. So similarly, time, it takes some 2-3 hours for making the template, for setting up the template, etc. But once the template is ready, okay, it creates hundreds of components, hundreds of pamphlets in a single minute. Okay. Whereas in office printer, the speed is good, but I mean you can just press print it immediately. But if you want many components, it takes long time. Okay. So this is the basic idea. Okay. So which printer is better? Which printer is cheaper? Okay. Is it offset printing which is cheap, or laser printing which is cheap? Is offset printing which is faster, or laser printing which is faster? Okay. The answer depends on the volume. Okay. If you want to print 2 copies of your thesis, you don't go for a offset printer. You go for a laser printer. You want 2 copies, you want 5 copies. Okay. Laser printer is faster and is cheaper because there is no investment time, there is no investment cost. Okay. But if you want 10,000 copies, okay, you want to make 10,000 pamphlets or newspaper of 1 lakh circulation. Okay. You don't go for laser printer. You go for offset printer. Although there is some time involved in setting it up. Okay. And some cost involved in setting it up. The scaling is very fast and easy. Okay. So that is same concept which again is applicable for 3D printing also. Okay. So for example, if you want to print this small pen, okay, a normal pen, plastic pen you have, okay, it takes probably 2 rupees in injection molding and probably half a minute to make it. Okay. In 3D printing route, it takes you almost like 4 hours to print and maybe 100 rupees to cost. Okay. So it's not cheap, not fast for large scale. Okay. But for a single part, okay, so if you designed a mouse, okay, and you want to test how the mouse looks and works, okay, instead of going for the injection molding setup and everything, you can just print it up, see how it looks, see how it feels. So there it is fast. Okay. So to answer that question, okay, is it cheap? Is it fast? Okay. Yes, for low volumes. Okay. No for production scale. Okay. So if you're talking about 5 components, 10 components, if you're talking about small volumes, 3D printing is both cheap and fast. Okay. But if you're looking for large volumes, if you want 100 components, 1,000 components, okay, 3D printing is neither cheap nor. Please skip that. Okay. So is it accurate? Okay. I think I mean so no, I mean compared to CNC accuracy of 1 micron, 2 micron, I don't think any 3D printer gives you so much of accuracy. Okay. But the bigger point it is improving every day, and how much do you need? Okay. I mean not every component you need a 1 micron accuracy. Okay. There are hundreds of components which you can survive with 20 micron or 30 micron accuracy. Okay. So it also depends on your need. Okay. And 2, it's improving every day. So for example, if you remember your first 2D printers, okay, dot matrix printers, that kind of dots, ding, 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 okay, it used to kind of go around making that lousy noise, okay, and it used to be so many dots and very difficult to understand and realize, okay. Whereas now, if you look at the quality of a 2D print, okay, very excellent, okay, in a similar fashion, although today 3D printing is little inferior compared to other methods, it is improving, and in many situations it is able to match and give you adequate surface finish and quality. Okay. Now, is it metallurgically good? Okay, again, I think I mean you have anisotropic property issues, you have troubles with layer debonding, etc. Okay, so but the point is again, not every component is a aerospace component where you have to put where I mean whether it is sustaining a fatigue life of 10,000 cycles or 1 lakh cycles, etc. Okay, so for many components today, for many requirements today, 3D printing is more than adequate for the required geometries, for the required strengths, etc. Okay, there are so there are, for example, some aerospace components, some coaching components, which I don't think 3D printing fully caters today. But even there, it is making good improvement. Okay, I mean there is a lot of improvement even in that examples also. I think, I mean, so just to put it, okay, so 3D printing is maturing into a long and I mean, kind of mature industry. So, okay, so for example, if you take today, there are a lot of these freeware open source also, where you go, you can build your own 3D printer in less than 20,000. Okay, using, I mean, all the material, in fact, how to tighten the screws, everything step by step, rules are step by step, guides are available in the market, in the websites, etc. here. Okay, I mean, you can go to these websites, you can just download, and in just 3-4 days or a week, you can create your own 3D printer in your house in less than 20,000. Okay, so that's the ease with which it is available today. Okay, and you have a lot of Indian suppliers today, a lot of foreign makes, etc. Okay, there are a good number of Indian makes today for 3D prints. Okay, and then so the whole idea, okay, is 3D printing is how it is transforming the fabrication and kind of making the product design very simple, etc. Okay, so again, I think, I mean, this is a for example. Okay, you can make your own 3D printer at home. Okay, and you can even not just that. Thingiverse is one of my favorite websites. Okay, where you can go download thousands of pre-CAD models. You just download, print them in your home using your own 3D printer. Okay, so they're free, all of them are freely available. You just go there, download, and then use those models to print in your own 3D printer. Okay, so and also kind of, for example, during the COVID protocols, okay, so there was a dedicated website, okay, created by NIH, National Institute of Health in US, okay, to share 3D printable models for COVID, for example, okay, clinical use in COVID. Okay, so that's kind of also an example, I mean, of how 3D printing is not just, I mean, a hobby or a niche area, but a mainstream also. Okay, so where people have used it to meet immediate requirements, where they were acceptable by the medical community in a comfortable manner, etc. Okay, I think again that goes there. So I think, I mean, this is another nice example. There is kind of a lot of this was my earlier slide. They have finally made 10 lakh face shields. Okay, so where they were grouped around and made 10 lakh face shield in the initial days of the COVID to meet the immediate requirements, etc. Okay, so kind of, I mean, a nice example of how a decentralized manufacturing system, okay, can help augment the requirements of a large scale manufacturing also. Okay, I mean, you have it being used for visualizing mathematics, for example. Okay, and so again, this is a nice book and a website. You can very well go and look at it. Okay, where it gives lot of 3D printed samples and geometries for visualizing mathematical concepts. Okay, so polyhedra components, okay, curvature components, knots, surfaces, etc. are nicely demonstrated. Okay. And I mean, so you, not just that, you also have the vendor modeling of 3D printing coming up. Okay, I think in US already it is pretty popular, but even in India also it is picking up, where you don't have to own a 3D printer. Okay, you just go there, create your CAD model, you upload your CAD model into it, okay, and select which process you want. They have tons of 3D printers with them. They will print it for you and they will post it back, 3D printed component in 3 days to you. Okay, so that's kind of also that model which is being very successful. 3D Shapeless is one good example. I think there are similar good vendors in India also. Okay, where, I mean, so where vendor model of 3D printing as a service also is slowly picking up. And I think, I mean, so to conclude, okay, so kind of bringing the whole context. Okay, so I mean, when it comes to Make in India and this thing, okay, I don't think in mass production, I think, I mean, China is way ahead of us in terms of big factories. Okay, I mean, I don't think India can catch up to China in mass production. Okay, but and frankly, I don't even want India to compete and match there. Okay, because I also believe the China's big factories come at a considerable labor practices and considerable difficult working practices for the labor, etc. Okay, I don't want Indians to imitate that. Okay, I don't want labors to be exploited. Okay, I mean in that manner. Okay, I would rather, if you look at India, okay, where the India strength vis-a-vis China has been always in the service industry. Okay, so I have excellent service industry. I mean, whether it is IT, whether it is hospitality, whether it is services, whether it is automobile. Okay, all these okay has been excellent in India vis-a-vis China. Okay, and I think if you look at the future, okay, it is not mass production, but it is mass customization. Okay, where maybe producing 100 different components, but each is unique as per the requirements of the user. Okay, so nobody wants the same car any longer. Nobody even wants the same chapel any longer. Okay, so you want to customize your own chapel. Okay, you want to customize your own bag. You want to customize your own chair. Okay, that every customer wants to do that. Okay, and I think that's the future. Mass customization is the future. Okay, and that happens with a mixing of production and service aspects. Okay, and I think if India wants to kind of look into the future of manufacturing, I think that is the game we should focus. Okay, where you build upon the unique strengths in the service industry with the production facilities, with the I mean kind of tuned and tailored production facilities, and I think that is where India should. And I mean that's the future of manufacturing, and I think that should be where India also should be focusing. Okay, in that mass customization. Okay, and in that essentially additive manufacturing is the ideal tool. Okay, mass customization definitely is the future of manufacturing and the customer reality. Okay, I think additive manufacturing is the ideal tool when it comes to mass customization. And there I believe so additive manufacturing in general also has a significant role to play in the future manufacturing evolution, etc. Also, okay, and I mean kind of how if India wants to create a sustainable ecosystem for manufacturing, Atmanirbhar, etc. Okay, I mean, so these are words. Okay, but I think I mean, if we put our energies and passion into it, it is possible. Okay, I think that's kind of summarizes it. Okay, so I think. Okay, so some of the topics I will again repeat tomorrow in greater detail, in the metal context. Okay. But for today, I will just pause here, okay, and maybe take any questions from the audience.
Okay. Thanks. Thank you, Professor Surya. Yeah, if there are any questions, I see there's one question in the chat box. But if there are any other questions, maybe you can unmute and ask. So in the meantime, I'll just ask the question which is in the chat box. So this is by Suraj Gupta. He's asking, is thermal stresses available in SLA and DED?
I mean, are thermal stresses there? Oh, definitely. I think thermal stresses in SLA, I think it's a liquid photopolymerization process. So it's not significant. Okay. See, thermal stresses by definition happen wherever there is a thermal process. Okay. In SLA, it is a chemical process. It's not a thermal process. Okay. So photopolymerization is a chemical process. So the heat involved is not significant. So you usually don't have too many. Of course, I mean, chemical process can have endothermic reaction and can lead to thermal. Okay, but in general, SLA does not have much of problems with thermal stresses. What is the other technique? SLA and
DED.
DED, of course. DED has hell of thermal problems. Okay, I mean, so one of my complete project with, for example, Boeing is on residual stresses and thermal distortions per DED process. Okay, I mean, so in DED it is a hell of a problem. Okay, there are there are issues, but they can be addressed and they can be solved. Okay, it's not like a complex problem. Okay, but yes, I mean it needs to be addressed, and that's, for example, one of our own areas where we are doing research is in the DED for addressing residual stresses and distortions.
Okay.
Hello, sir.
Yeah.
Go ahead.
Sir, good afternoon, sir. Sir, as we are handling metal powder, which are safety precautions we have to take?
See, I mean, I think usually safety precautions come in hand. So typically, I mean that you need to wear a mask, you need to wear a gloves. Okay, so such kind of precautions are needed. Okay, so in fact, even when we operate metal powders, because I mean, if you are careless, you can inhale and it will sit in your body. Okay, but I mean, it's not like, I mean, as if you are going to a biological laboratory where you have to wash your hands and feet about 10 times after you come back. Okay, I mean, it's just that metal powder should not come in direct contact with you. So gloves and masks usually take care of, I mean, and goggles take care of the things comfortably.
Okay, thank you, sir.
Okay.
Hello?
So, yeah, go ahead.
Sir, I have one doubt.
Yeah.
So, what is this dimensional stability of product?
Okay. Again, I think, I mean, see, you have to remember additive manufacturing is a umbrella of processes. It's not a one process. Okay.
Yes,
So, I mean, so different processes have different surface finish. So, for example, SLA, where you are using liquid, gives you excellent surface finish. Okay. And where, for example, VAM process gives you the other extreme. Okay, and where, for example, if you're using powder, it gives you medium surface finish. Okay, it depends on the process. Okay, so but I mean, simple. Liquid is the best surface finish. Powder is comparatively better, and wire is the worst. Okay, so that's kind of the thumb rule, you can say. Okay, so and it depends on the process which you are using. Okay, so it's not like single system surface finish and accuracy. Okay, it varies by the process. Okay, it varies by the process.
Okay, so one question. Can we mix the metal chips in FDM with the plastic material to form a metal matrix composite? Is it possible? So can we mix the chips which are produced in machine, metal chips, with the with the plastic material which is used in FDM to form a metal matrix composite? Is it possible, sir?
It is possible. There is a process called MIM. Okay, it is called as metal injection molding. People are already doing it. There is a company called Marcos which does that. What it does is it mixes 80% metal powder in 20% plastic media and extrudes to powder. I mean, through the nozzle. Okay, it is possible, and already people have been doing it. Okay, but there are again. You need to, I mean, so you need to worry about the contraction and all, right? Okay, so you cannot, I mean, just extrude metal powder. You have to mix with some at least 20-30% of plastic. Okay, now if you are mixing 20-30% plastic, is it still called metal? Okay, and I mean, what about the, even if you remove the plastic through furnace? Okay, what about the contraction of 20%? Okay, so what happens to your dimensional accuracy and cracks? Okay, so there are challenges, but I mean, yes, it's a new process which has come up. It's fairly recent. A company called Mark4, okay, has created Mark4X, which does the same body image. Okay, it is possible in theory. Okay, but I mean, people still challenges are about the strength and the dimensional accuracy that people are working.
The same which Dr. Ganga has. So,
Correct.
yeah, anyway, we have a session by Dr. Ganga, then maybe he'll be able
Good.
to spend more time.
So he would be able to talk about how these composite printers can work, MetaMask composites can be created using this.
So there is one question that, sir, whether SLM is a direct energy deposition or powder bed fusion?
SLM is direct powder bed fusion. Okay, so essentially what happened, people started selective laser sintering, then people started selective laser melting. Okay, SLS, SLM. Okay, then I think to get rid of this quarrel, and people were not sure what qualifies as melting and what qualifies as sintering. Okay, so then they said, okay, melting or fusing, I mean, sintering does not matter. It is fusion. you fuse the particles together. Okay, whether partially, then it is sintering, fully it is melting. So commonly people are using the word fusion to address both fusion, sintering and melting together. Okay, so both are powder bed fusion. Okay, you fuse the particles, half of them it's SLS sintering, you fuse the particles fully, it's melting. Okay, but so it's both of them are come into the same umbrella processes. Okay, it's SLM, fused powder bed fusion.
Yeah. Okay. Last two questions which are there in the chat, then we will stop and maybe we can continue tomorrow.
I think tomorrow also we can have some more questions.
Yeah.
Okay, so tomorrow.
So here the first question is, up to what extent we can use FDM from material perspective or melting point of view?
See, I think melting point of view, currently existing systems, most common systems which use FDM are ABS and PLA waste, which gives you around 190, 200 degrees centigrade range. Okay, and people are also have tried nylons which come around 300, 350. And there are recently some more high compression nodules, 400, etc., which are possible to make peak material also. Okay, so there, so standard printers are 200 degrees types. Okay, and there are these niche high-end printers which allows you to up to 400 degrees also for peak and I think nylon and peak are very common. Okay, so you can use up to 400 degrees are currently what you can available in the market. Okay, which you can use. Okay, and that covers most of the materials.
Yeah. Yeah, the one we have, it has a nylon and other peak type of materials.
Correct.
Where the temperature can go up to 400 degrees Celsius. So one last question, that do we need to give tolerances while designing for 3D printing? This is by
of course, any manufacturing process requires tolerances, including 3D printing. Okay, but the catch here is which 3D printing method and accordingly how much tolerance you will give is the question. Okay, so if you are a jewelry manufacturer using SLA or liquid as a raw material, your tolerances can be very small and very close. Okay, because the process is fairly accurate. But if you are working on metal powder, then the tolerances need to be little high. Typically, it goes up to 40-50 microns of that nature. Okay, so yes, tolerances has to be given. Finish machining is required, but it depends on the process how much you give. Okay, so if you are talking about an accurate process, you can give less tolerances or more tolerances depending on the process in hand.
Okay, I think we'll stop here. There are we can continue this tomorrow. So with that,
I think you are muted, Dr. Omkar. I'm not able to hear you.
Yeah. I think with this, I don't see any more questions here. Thanks.
I think
we can continue.
If there are more questions, I think anyway it's time. So if there are more questions, let's discuss them tomorrow.
Yes.
Okay.
Okay.
All right.
Thanks. Thank you, Professor Surya. And yeah. So now we have a short break. We will be beginning the next session at 4 o'clock. So we have around 20-25 minutes break. So we'll just stop here. So again, join us back at 4 p.m. sharp, and then we will start. Okay. Thank you.
Yes.
Good afternoon, Abdullah. No, there are two, three things. One is, see, this you have assembled one 3D printer, no? So, from where did you buy that? Oh, through Amazon you have purchased. Okay. Mm-hmm. Okay. No, I was wondering if there are any vendors who can supply this. Mm-hmm. No, no, we need a very simple and a very low cost printer. Hello? No, no, what we need is something which is very low cost, around 25,000. So for that, I was wondering if you want to generate some quote and invite. If there is a quote, it would be ideal. If somebody can give a quotation, so just check if somebody if they can generate the quote. Within 25,000. Hmm. Hmm. That is also fine. Yeah. So you just share the this thing, no? Like if you have purchased on Amazon or somewhere, there whatever the price, that screenshot is also fine. No, no, not now. By tonight or maybe tomorrow you can send. No, no, take your time. No, no hurry. When today? Hmm. Okay, okay, fine. Hmm. Okay. Uh-huh. Mm-hmm. Hmm. 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 Yes. Hmm. Sure, sure. Yes. Okay. Then you have to assemble. Okay. Okay. So you try to get code from both the places. Okay, whichever is convenient, we will do it. Mm-hmm. Yes, yes, it is there. So I have sent your email ID also for Did you get any mail from 3D Experience? Huh. No, not for the class, for that software, CAD modeling. I think they will send. I think today, Saturday, Sunday, they won't activate the licenses. No, not Mojo. They will be teaching that 3D Experience software. 3D Experience. Hmm. That's what. They will send the email with which you can access the software. Hmm? Uh-huh. Okay. Hi, good afternoon. Good afternoon, Dr. Sajan.
Yeah, good afternoon. Yeah.
Yeah, hi.
Hi, how are you?
Fine. How are things?
Hello? Am I audible?
Yeah, yeah.
Yeah. So when are we going to start now? It's 4, I
Yeah,
think already.
we'll start. We'll just wait for a couple of minutes. See, actually, there are 45 participants. So we'll just
Okay.
wait for 1 or 2 minutes. So then we can start.
Sure. We'll wait.
Yeah.
So your offices are open?
No, we are still.
You're mute. You're mute.
Yeah, no, not yet. We are still at home. So
Oh, okay.
classes are still running on time. So hopefully
That will remain, I think, for next semester also.
So how are things there?
Our scholars are back. They are here since last, I think, 5-6 months. They came back in January.
Yeah. Okay.
I think February. Yes, and then they are here.
Okay.
They MTech second year and PhD scholars are here. So our office again started, I think, from 16th. So I'm in office only, but
Oh,
we are going to the labs now again.
Oh, good.
From yesterday.
Yeah. Good. Okay, so I think we can start. People may join now. 34. Okay, so good afternoon. Welcome back for the fourth session and the final session of today. This session will be conducted by Dr. Sajan Kapil from Mechanical Engineering Department at IIT Guwahati. So maybe I request our student volunteer, Mr. Kamal, to introduce the speaker, and then Dr. Sajan, you can take over. Okay.
Sure.
Okay.
Yeah,
Thank
over
you,
to
sir.
you, Kamal.
Okay, sir. So I feel extremely delighted to introduce young and energetic professor in manufacturing stream, that is Dr. Sajan Kapil. Dr. Sajan Kapil is working as assistant professor in Department of Mechanical Engineering at IIT Guwahati. He has done his undergraduation from GB Pant Engineering College, masters from IIT Guwahati, and PhD from IIT Bombay. His research interests are additive manufacturing, welding process, manufacturing automation, CNC, CAD and CAM. Dr. Kapil has 5 patents and orders 16 research publications in peer-reviewed international journals, and he achieved all of these remarkable achievements in just a span of 8 years. So we are very delighted to have his section. So I request Sajan sir to come.
Yeah, thank you, Kamal, for your nice words. I'll just share my screen. Just let me know whether it's visible. Yeah, now is it visible?
Yes, sir.
Yes.
Okay, fine. So let us start. So once again, thank you very much. My name is Sajan Kapil. I'm assistant professor in the Department of Mechanical Engineering, IIT Guwahati. So today in this session, I will give a lecture on a very interesting topic, that is powder handling system for DED. Because I have seen many powder bed systems are getting developed in our country nowadays. But now I think the next will be the DED. The target will be DED of many of the researchers and the one who wants to develop the things. So The first step comes here is the how they handle the powder, and I'll just give you some very interesting information in the beginning itself. I'll discuss about that later on as well. Like for example, electron beam based system, there is no DED till now, because usually the conventional DED systems usually handle the powder with the help of some pneumatic mechanisms, such as pneumatic gases, such as organ and all. But the requirement in electron beam or the vacuum environment is to have a delivery system without any pneumatic gas, because that will lose, otherwise we will lose the vacuum. So our goal will be today to see the overall what are the all the mechanisms available in to handle the powder for DED particularly. So that is going to be the content of today's lecture. I'll start with a brief introduction to the additive manufacturing, not very detailed, and then I'll discuss about the DED, directed energy deposition. I'll discuss about the powder handling in DED, powder metering and conveying devices, powder delivery nozzles, powder delivery nozzles of three kinds basically I'll discuss, the pneumatic designs and the non-pneumatic designs, and finally I'll discuss briefly about the powder delivery nozzles and their stream characteristics, the process parameter, those are really affecting the characteristics of the stream when the powder comes out of the nozzle. And in the end, I'll conclude this presentation with the remarks on the challenges and the conclusions. So, by ASTM, we already know that the additive manufacturing has been classified into 7 categories. The first category is the wet photopolymerization. Second is material jetting. Third is binder jetting. Fourth is material extrusion. Fifth is sheet lamination. Sixth is powder bed fusion, and the last one is DED, directed energy deposition. So what happened? I'll just quickly explain about each process so that we'll have clear idea what we are going to discuss in the next subsequent slides. Like in wet photopolymerization based process, they used to have a liquid tank full of photopolymer liquid material, and from the top a UV light falls onto it. Wherever the UV light falls, that portion of the photopolymer gets cured because of the reaction start, the photopolymerization start, and here typical power which we use is approximately not more than 40 watt. It's very low power laser we usually use, or even sometimes it's in milliwatt, 40 milliwatt also. Very low power laser is required, because here just we want to initiate the photopolymerization process. The next is material jetting. Material jetting could be like you can inject the molten material such as the liquid water itself on a bed which is very at a very cold temperature, or if it is like photopolymer material, you can inject the photopolymer material, and from the back immediately a UV light can cure it. So it is just like in the case of aluminum, and subsequently we cure it somehow. Here, typical power required is more than this 40 watt, because here we need instant curing if I talk about only the photopolymer based process. Next is binder jetting. In the case of binder jetting, we used to spread a layer of powder and then we inject the ink on it. So binder jetting is the name given by ASTM. I rather prefer to call it as ink jetting, because the ink can be having the binding material or it may not. Like for example, if you spread a layer of maybe cement like material and just dropping the water droplet somewhere. So water doesn't have any binding agent, right? So wherever but the water will fall on the cement like material, that will get cured. So of course, in some cases, like if you want to spread a layer of just sand, then the binder itself can have some binding particles also, and they can join the particles together. This process is also called as 3D printing, the binder jetting one. This was first developed by MIT in 1990s. Then the next is material extrusion. In the material extrusion, we used to extrude the material in the molten form through a tiny orifice. In some cases, like when the construction material like cement like material is used, again the orifice is tiny, but material is not in the molten form. It is actually a slurry, and that we extrude through a tiny nozzle. This is the most, I think I'll say, exploited additive manufacturing process, and I'm sure many of you have already seen it. The process following to this is FDM, fused deposition modeling. Then next is sheet lamination. Sheet lamination, what we do in sheet lamination, we join the sheets one over another and then build the part. But as the raw material is in the form of sheet, you can imagine immediately that if you just join the sheets together, you will end up making either cuboids or cubes. Hence, a subtractive process is definitely required. So there is no sheet-based process. Only, I mean, all these sheet-based additive manufacturing processes are hybrid in nature. They use a subtractive process also along with it. Like for example, loam laminated object manufacturing, you put one paper sheet, another paper sheet over it, and then you bind them together. And how the binding mechanism there is that on the bottom layer of the top and the top layer of the bottom, one of them used to have the thermally activated glue. When the sheets comes together and a thermal load is applied on the top side, the sheets together got joined. And of course, then after joining, you need to perform a cutting operation to carve out the region that is not a part of the main object and the region which is part of the main object. Here again, we sometimes use laser to cut this material out. So the power is typically higher than the laser extrusion. Then we talk about the powder bed fusion. In the case of powder bed fusion, we spread a layer of powder and we write from the top by using a laser beam. Wherever that laser beam falls, that portion of the powder get melted and got fused with the previous layer or the substrate. In this case, typical power, like in IIT Guwahati, soon we are going to have a machine that is having around 600 watt power. It's quite high, but I have not seen the machines with a single laser higher power than 600 watt. Then the next process is directed energy deposition. The directed energy deposition, in this process, the energy beam, it can be arc or it can be laser or it can be electron beam, creates a molten pool in a substrate, and that in that molten pool we feed the raw stock material. The raw stock material can be usually in two forms, either wire or powder. These are the two typical forms. Wire we are not going to discuss today. Our focus will be powder. Okay, so typically the power required here is approximately up to 6 kilowatt. I have seen the machines which are usually used to have the power around 6 kilowatt. So the interesting thing here is that ASTM has aligned these processes from left to right, not randomly. They have aligned them based on the energy consumption or the energy required to, for the process. Here you see around 40 milliwatt laser is required for the wet photopolymerization, and on the right side, a DED process uses approximately 6 kilowatt laser. It's a quite very high power laser here. So now, as our focus is now today mainly on DED, let us discuss about this DED first. In another classification, if I talk about only what are the different ways of making the metallic object, usually the DED comes first into the picture. Then of course, powder bed fusion, that is good for making very small objects, but not very large.
Sir, your voice is not audible.
Means I think there's a network issue. Sir will be joining too.
Okay, I think he's joined.
Hello.
Hello.
I think I lost.
Yeah.
Yeah, it's now audible, sir.
Yeah, I'm sorry, I lost because I have to refresh a home button here and it happened. I'm sorry about it. So where was I? Can anyone please help me? What I was
Yes.
Near the powder bed fusions. Big
on this slide.
turbines. Not anything.
Yeah, on this slide.
In this slide only, yes.
Okay, thank you. So fine, yeah. So I was telling that what are the processes usually used to realize the metallic objects. So as I have already explained these processes in detail, DED is the one which is very much now suitable to make the large scale components. Of course, the powder bed fusion is the most popular one, but to make the complicated small products, when it comes to the large product, of course, we have to go for DED. Then the sheet lamination, sometimes used, we prefer to make the tooling. Many people have tried this. Then bounded metal extrusion and cold spray, not really very popular, but still quite useful for making the metallic objects. So in the DED, the principle is selective deposition of the material in a substrate. It uses deposition nozzles. The deposition can happen either through the wire or powder as a raw stock material. Okay, so if we use powder, electron beam is not preferred, only laser is the available option with us. Electron beam, why it is not preferred? Because it happened in the vacuum and there is no, maybe on the laboratory level there are many setups. Even in IIT Guwahati we have developed one. If time permit, I'll show you in the end, but not really on the commercial side I have seen any system available for electron beam DED, because the delivery nozzle used to carry the powder along with the argon gas, and that will lose the vacuum, nothing else. Then of course the state of fusion is fully melting. You completely melt the powder and get the fully dense part by this process. So directed energy deposition, which is the other names for this process, the DED, are also direct laser deposition, DLD, laser consolidation, laser engineering net shaping. This is a trademark basically, it is by Optomac, direct metal deposition, and 3D laser cladding. And of course, by I also prefer to call it this technology as powder feed laser additive manufacturing. Okay, so there are basically 3 steps in DED. First step is to create a small molten pool on the substrate by utilizing a focused laser beam. Then we inject the build material or raw material into that molten pool. And of course, when you are injecting the raw material into the molten pool, you require a relative motion between the DED nozzle and the substrate. That relative motion we usually give by a robotic arm or maybe a CNC machine. So overall, how does it look like? As you can see in this diagram, this completely covers what are the subsystems for the DED. So basically, if I talk about the powder feeding unit, that is our focus today, it used to consist of 3 subsystems: the powder metering unit, the powder convenience unit, and the powder mixing chamber, and of course, and powder delivery device. So what happened in the metering unit? We measure the right amount of powder from the hopper or from the reservoir, and then take this powder and deliver it to the mixing chamber. Now, how we are delivering, how we are just taking this powder from this end to another end, used to be done by the conveying method we are using. So the powder convenience method, here what you are seeing in this picture is by argon gas. It is pneumatic method. So argon gas is going here, you can see it is going like this. It is taking right amount of powder from this chamber and right amount of powder from this chamber and taking it away into the mixing chamber, because there are powder number 1 and this is powder number 2. When they come here, they got mixed, and then further the same argon gas used to carry it till the end of the delivery nozzle. Now once it reached the delivery nozzle delivers this powder towards the molten pool. So only 3 systems are there. So like I have mentioned already, as our focus today is powder handling in DED, let us first give a classification to this process. So like briefly I have explained, the powder feeding unit can be classified into 3 categories or 3 types: the metering unit, convenience unit, and the delivery unit. The powder convenience unit, the powder metering unit can be of aspirating or dispensing type. It can be based on the screw or auger, or it can be based on the feeder wheels, or it can be based on the electrostatic. And to carry the powder, to convey the powder from one end to another point, the powder conveying device could be mechanical method or it could be a pneumatic method. The mechanical methods are usually by vibration. You vibrate and then transfer the powder, or it can be based on screw, or there are some gravity used for that. Now, how to deliver this powder? Okay, powder has reached to a nozzle. Now, through that nozzle, it has to reach to the molten pool. That is the job of powder delivery devices. The powder delivery devices could be gas assisted, vibration assisted, and gravity driven. The gas assisted powder delivery nozzles could be further divided into 4 categories: off-axis nozzles, continuous coaxial nozzles, discrete coaxial nozzles, and central feed nozzles. On the other hand, the vibration assisted nozzles could get vibration from ultrasonic range, or it can be acoustic vibration. The last one is the gravity driven. Very few systems are there based on gravity, but here in IIT Guwahati we are trying to develop a gravity based system which can do without involving any gas, the metering, conveying, and the delivery of the powder towards the molten pool. So this is the gravity-based system. Now let us try to discuss about each and every process in detail. So first is powder metering. Usually when we measure the powder, the conveying unit used I'll discuss simultaneously, because I'll not discuss it separately. So that is why powder metering and powder convenience devices are discussed now. Will be discussed now. So the first method which I have mentioned for powder metering and convenience system are shown here. This is based on screw and auger or oblique auger methods. So use of screw for conveying the powder, metering and transportation in DD process was suggested as early as in 1988 by the William Steen. So William Steen, I believe, was the inventor of the DD system, because he is the one who started, as per my knowledge, the laser cladding system, where he used to have a CO2 laser in 1988. I have read a paper of it, where the CO2 laser used to create a molten pool, and from the tube, just simple tube from the side, spray the powder particles into the molten pool. So he only that time used to prefer to use a screw-based system, which rightly measure the right amount of powder and deliver it in a chamber. The design consisted of basically a motor which is driving a screw which pushes the specific amount of powder into a chamber. When it goes into a chamber, from where it gets picked by the gas, and that carries it. Means the gas is the conveying system here. So let me just explain it to you with this diagram which we have made. We have a motor, and this motor is attached with a screw, right? As the screw is rotating with some RPM, let me consider that its speed is some rotation per minute. The right amount of powder will be delivered to this chamber. If the speed increases, of course, more amount of powder will be delivered to this chamber. And if the speed is less amount of powder will be delivered. Now, once the powder reaches to this chamber, an inert gas used to come from the top, and that carries this powder, whatever powder available in the chamber, with it towards the molten pool. So this is an example of the screw and auger-based powder metering system coupled with a pneumatic conveying system. Okay, so if you want to use two powder, or you want to use two powder A and powder B, and you want to mix them, and then you want to deliver towards the molten pool, then of course you can have two such screws. Like here, this is the powder 1 and this is the chamber for powder 2. Now there is a motor which rotates the screw and delivers the powder towards a chamber, and where we collect this powder A and powder B, they got mixed by a stirrer, and then the powder is conveying further through a pneumatic gas. The next is the vibratory method. Now here the amount of powder will be measured by the vibration. And how? Use of mechanical vibration for metering and transport granular material is very common, but may not be very popular in additive manufacturing. But handling the powder material is quite popular in this way, and it is popular in most of the time in agriculture and food processing industry. However, like I said, that in the metal additive manufacturing, its use is quite rare. So what happened? There is a hopper like this. Sorry, this is the hopper, and the powder is falling into a chamber in this tube-like structure. I can give the vibration to this, that is back and forth like this, and also I can give a vibration in another direction. Means that the vibration in the longitudinal direction and in the transfer direction. Based on the amplitude and the frequency of the vibration which we are giving to this tube, will decide how much powder should get delivered to the next unit or whatever. So amount also, if I give a high amplitude of vibration, the amount of the powder which was going per second or which was transferring per second will change. Hence the powder metering is here done by the vibration. So vibratory convenience using the acoustic vibration here. Here there is an acoustic vibration. Okay. If you want to use two materials, of course you can use two materials. This is material 1 and this is material 2. And these two materials we can we can rightly measure, like I have already mentioned. The convey here and the measurement is done by the vibration, the appropriate frequency and the amplitude. You can decide how much powder number 1 should go and how much powder number 2 should go. They will go into the mixing vessel, they mix it and deliver further. Next is the gravity based methods. Similar to vibrating methods, use of gravity method for powder handling in DED is very rare. It's not really very common. Not, at least the commercial systems are not really easily available. So a challenge associated with gravity based system is the phenomena of jamming. So jamming stops the granule flow for system operating under gravity by forming arch like a structure. So what happened, as you see here, this particular picture shows why jamming happened, and there is a thumb rule for that. This arch, it depends on the radius of this small tiny particles. This is the radius of these particles and the radius of this opening. Okay, I think it is 3 times of this, 2.5 or 3 times of it. I'm not sure, but there is a thumb rule for that. So what happened? If the diameter is less than the critical value, the powder used to form an arch like this, and this arch is quite stable. And now you can see the force is balanced, and definitely it will not allow any powder further to go until you will not disturb it. I mean, you just push it away, and then maybe
these
it may start. But
waitlist candidates,
at some
we
point
have
of time, it will get
to
jammed.
send them.
So how the gravity tubes look like? They look like this. These are the very long pillars of the powder, and there are hoppers on the top. They used to flow here and then they get delivered. If the critical radius is larger,
And
the
also we
flow
have
will
to
be
send
easy.
them what is their
There will be no issues.
sequence.
Again,
What is
these
their
are the
number?
conveying system. Okay, how do we meter? Because
How
measuring
much
here
is
may be
their
a
waitlist
difficult
number?
task. So for metering, of course, you can use the screw based system, which can transfer the right amount of material into a chamber where it gets mixed, and then further we split the powder so that you can form a conical foam. I'll explain you why conical foam nozzles are at all required, and then deliver these
See,
powder particles through a
that
chamber
day
which
when
is
you
in
send
this
me the
shape.
email,
It is a
no?
coaxial nozzle.
So I think even now
Then
that
through the
can be
coaxial
done.
nozzle,
See, if
powder
you
is
can
transferred.
send
And you
me the
see
Excel
it
sheet
is
with the
happening
name
under
and
the gravity
email
only.
ID,
So it is basically a
that
gravity
is good
based
enough for
handling
me.
system. Measuring is done here by the screw
One
gun.
Excel sheet where
Okay.
the serial number or
The
their
powder
waitlist
conveying
number,
is happening here by gravity.
and then
Now I'll
their
discuss a little bit about the
email
pneumatic
ID, so that I
methods.
can mail merge and
So
send
out of all the
immediately.
methods, pneumatic powder
Okay.
feeders are the
So just
most popular
the
in
serial
DED
number, their
and laser
application
surface
number,
cladding in other, because
their
DED
name
and
and
laser
mail
cladding
ID.
is not really have much difference. In
Okay.
cladding we deposit 1 or
So that
2
if you
layers.
can
In
send
DED
it,
we deposit
I'll send it.
the material in the region and realize the entire part. So all commercially sold DED units employ this mechanism for powder metering, conveyance and delivery. Now, what are this pneumatic method in principle work by creating a pressure difference within a system which facilitates metering and conveying of the powder feedstock. So how it works? Let me just show you the one very popular system. Here, when a compressed inert gas goes, right, it is going from this end and it is going through this. Now there is an index plate on the bottom. This is the index plate. This top one is the index plate and this bottom one is the base plate. There is a hole in the base plate. This hole is fixed. It doesn't move. Fine. Now inert gas is coming here. While in the index plate, there are multiple holes. There is not only one hole. And in the base plate, only one hole. And this index plate keep on rotating like this. Okay. So what happened? When this hole come coaxial, or just when the hole is just at the is aligning with this bottom hole of the base, the powder will transfer, of course. Otherwise, the powder will be blocked. So, for example, this index plate in zoom version looks like this. Fine. If the hole is matching, the top hole of the index plate is matching with the hole of the base plate, then the powder which is coming from the bottom will take the gas coming from the top, the gas coming from the bottom will move towards the top, and when it is moving from bottom to top, it will carry some powder from here, from this chamber, and it will take it away. Correct? Now assume that the speed is very slow, very slow, and at the first coincidence it is taking away some a amount of material. Assume that. So if the speed is very slow, this hole which is right now coincident with the bottom one will take a longer period of time to again come and become coaxial with the bottom, with the base plate hole. Hence the delivery of the powder will be less. And if it is rotating with a very high speed, you can imagine even that all the time any of this hole will be aligned with the base plate, and hence it will always transferring the material. Hence the material transfer will be high in that case. Right? So this is the most popular one, because here you are controlling it just by one parameter, and that is rotation of the index plate. If index plate is not rotating and the base plate hole is matching with this portion where there is no hole, then no material will get transferred. Also, there are some other methods which I have just explained is the most popular one, but there are few others also. The fundamental is same. The fundamental I have explained earlier was, in pneumatic method we have to just create the pressure difference. The pressure was high in the previous case at the bottom and low on the top. When the hole matches, due to the pressure difference, gas flows and take away the powder. The same thing can be done by the vacuum also. Assume that now in this one there is a vacuum line here, right? It takes the powder from the bottom groove. So there is a groove here. Okay, there is a groove. Fine. Now assume that if the vacuum is there, maybe some P pressure is there, that is lower than the atmospheric pressure, and this is the hopper, and this bottom, this groove disc, it is rotating, it is continuously rotating, and there is a fixed disc just to keep it. Now if the disc is rotating, what will happen? There is a hopper here, and the material is just pushed towards the groove under the gravity. If it is rotating, definitely some powder will get filled into the grooves, of course. Now if it is moving with a very slow speed, assume. Now slowly this groove will come under this pipeline also, which is taking away the powder because there is a vacuum here. But due to the slow speed, less material will get transferred. And if it is rotating with a high speed, more material will be available for under the vacuum line, and it will keep away sucking more material, and hence delivery rate will be high. So this is one of the method used. The next one is the inert gas. With the chamber in which there is a rotating wheel, like you are seeing here. So what is happening? There is a hopper here on the top. This hopper has a lot of material, that is powder, and there is a valve. When the valve opens, for example, the powder is transferred into this chamber. So let me give the chamber name. This is chamber 1, this is chamber 2, and this is chamber 3. Chamber 1 is always filled with the material. Chamber 2 is filled with the material as well as the inert gas, and chamber 3 is empty. So what happens when this chamber 1 comes on the top, or any chamber comes here? The powder is getting filled into this volume. Assume that this is volume V1. Then this, because of the rotation of this blade, this material will get transferred to now this chamber, that is chamber 2. And now as there is an inert gas coming from this end, it will take away some material and it will go towards the wherever required. Now, and after delivering it, of course there will be nothing available, and there will be empty chamber here. The rotation of this black color portion will decide how much powder should go. For example, it is not rotating, means nothing will go. If it is rotating very slowly, less material will go. If it is rotating very fast, means this volume V1 is transferring with very high speed, many times in a second towards this second chamber, and the powder will be taken away very fast. Other method is electrostatic method. In the electrostatic, basically the electrostatic valve retards the free flow of the particle. Now, how does it work? It's very, very interesting. And I believe that if someone wants to want to develop a micro level powder injection system, this is the one. I believe this is the one. So how you can do? You can have the gravity tubes, like you fill the powder on the hopper. Fine. Now, as the diameter of this tube is quite large as compared to the particles, not like 3 times or 4 times, it's really high, then definitely the powder will keep on flowing, and it will flow like with a very high speed. But that is not the requirement. I want to stop it also. So what I can do, assume that this powder particle is electrically conductive. That is important. Huh? If it is electrically conductive, I can put some electrodes here and generate and provide some current to them. So what will happen? This particle will get stick towards the wall. As the particle will get stick towards the wall, what they will do? They will reduce the area which was available to flow the powder which was coming from the top. Based on the amount of current which we are giving to these electrodes will decide how much area should block. It may also happen if you give sufficient amount of current, it can block completely and no powder will flow. But if you are giving it in a very controlled manner, maybe you can give in pulses, open, close, that thing can happen really very fast, because this is not a mechanical valve, and the life of the valve will be really, really high also. So in the pulse, that is, I have not seen any literature, that is just my idea. Maybe you can think about this in pulses and just transfer the material in pulse with a very tiny tube, and maybe you can think about transferring the nano particles. That could be the best method for that. But anyway, so now if the area is getting restricted, based on that you can transfer the material. Here the metering is so simple. Okay, so the cluster particles added to the glass ball reduce the diameter of the flow column, thereby reducing the flow. Based on the amount of power you are supplying, you can do the same thing. Now let us move to the powder delivery nozzles. Okay, so we have discussed about the powder metering and convenience devices. Now let us discuss about the powder delivery nozzles. Typically, you have seen, and I'll discuss, I think, in tomorrow's lecture more about it. Today I'm not going to discuss about why this type of nozzles are required, but I'll just give you the idea what are the nozzles available, and tomorrow I'll justify that why it is required, why people are doing it. And not only in this process, I'll discuss about the entire IIT manufacturing process. So conventionally, in the lateral feeding, in the powder delivery devices, total 5 types of delivery systems are available. First is called as lateral feeding. In the case of lateral feeding, we use a laser beam which used to create a molten pool, and in that molten pool, we feed the powder particles from the side. This is called as lateral feed or off-axis nozzle. The Professor William Steen, when he invented the cladding system, based on the thing I read, I could visualize this is the system, this type of system he first invented in 1988. Just a tube at the side, and it is called as off-axis nozzle. But still, these type of systems are popular and are used in the industry. I'll give you an example. The next is continuous coaxial nozzle. I read a paper of William Steen again in 1991. Immediately, I guess within 2-3 years, he has invented this particular nozzle called as coaxial nozzle. In the coaxial nozzle, we have the laser at the center, and the powder particles are delivered in a conical form towards the molten pool. Then the third one is discrete nozzle. Discrete nozzle means very similar to this continuous, but an approximate version of the same, like multiple nozzles on the periphery. If multiple nozzles are there on the periphery, what will happen? You can even use multiple powders, and you can just make the FGM in the XY plane. Then central feed annular laser. These are some recent achievements which I have found, but of course, here you need expertise in laser side. To develop all three on the top side, you can deal with the conventional lasers, and you need some innovation towards the powder delivery side, and that is, I think, easy for us because we don't really make a laser on our own in India. The another one is like number D and number E, what you are seeing here. In this, the powder is supplied at the center, and we usually have an annular shape of laser beam that got converged at the bottom. It's in annular form. So laser is not really a solid beam, it is annular. Now annular laser converting is a bit difficult task, and that more falls into the physics side. So assume that you have that kind of laser. If you supply the powder at the center, entire powder is trying to capture by the laser, and the efficiency of this system, I believe, and I have seen in some papers also, they claim also is quite high. The fifth one is central feed with discrete lasers. Now here you can, instead of using a conical laser, you can put 3 lasers also. I read a paper of China, they have used this type of 3. They did not even split the single beam into 3 and then converge like many of the German instruments are like. They just put 3 laser beam. They bought 3 laser source, put them together in such a way that they merge at a center, and from the center they supply wire. But assume that the same thing can be happened with the powder as well. So let us now, these are the types. Okay, now I'll discuss about, these are the ways of delivering the powder towards the molten pool in the powder delivery system. Now how the powder can be conveying towards the molten pool, to convey the powder towards the molten pool, there could be 2 methods, pneumatic method and the non-pneumatic method. Let us first discuss about the pneumatic designs. What you are seeing here is an off-axis nozzle, and it is used for the cladding purpose. You see that it's tilted. You know why it is tilted? I believe because when the laser comes, if it is vertical, laser may go back into the optics and destroy the whole thing. So it is slightly always tilted. Laser is never perpendicular. So you see that this particular nozzle here, it is transferring the material, and it is off axis. And this particular application is here, what you are seeing is for cladding. So feeding of powder oblique to the heat source facilitates the easy setup design. You need not to do anything. Just put a nozzle, bolt it appropriately. Lateral feed nozzles create an asymmetry in the powder temperature, laser intensity, and hence, of course, the movement pool will also be asymmetric. It will not be symmetric about any center, the temperature in the mold pool basically. So to avoid anisotropy in the DD parts and achieve high dimensional accuracy of the build, coaxial nozzles are preferred over the lateral feed of the nozzle. Off-axis nozzles are preferred for the cladding of cylindrical components on the rotary setup like you are seeing here. Why? Because here direction is not changing. You are just depositing in only single direction. It's just moving always like this. So the feeding mechanism here is side feeding. This I will discuss tomorrow in detail. But if the application is like this, side feeding is not at all an issue, and off-axis nozzle can work. But if you want to use it for the additive manufacturing where you never know where you can take a turn, you should use the continuous the coaxial nozzles. So the first one is the continuous coaxial nozzle. So this particular diagram shows how it works. There are 3 ports usually. It's a cross section. It's a cross section of the nozzle. The first pass or first channel is for providing the inert gas through the center, and the center part is the laser. Laser is coming from the top, and along with the laser light, inert gas also goes. Why inert gas is required? Because it may happen some particle are bouncing and going towards the optics of the laser. To prevent that, a jet of inert gas is supplied from the center. Okay, it is written also here, inert gas for optics protection. Then from another port, powder is supplied. Then this powder is also carried by the inert gas again. So powder is carried and it is delivered towards the molten pool. Then from the outer periphery, a shield gas is again provided, and that is to protect the molten pool. Now how it can protect the molten pool? It just makes an envelope around the molten pool, a nice envelope around the molten pool. Once it is protecting the molten pool, of course, the chances of oxidation will be less. So this type of nozzle you see are quite useful nowadays in the additive manufacturing, but a lot of gas consumption is there. One gas for optics protection, one gas for shield gas inlet protection, one for melt protection, and all. There are a lot of protections, right? Also, instead of having just a plain annular sides, some people used to provide the what you call the channels. Those are directing the powders towards the molten pool. And it has been found if the channels are used in the coaxial nozzle, the focal point is bit tiny. I mean, it can pack the material, pack the powder particles in a very dense area as compared to the conventional coaxial nozzle, which is without the channels. So here you can see the machine conical grooves on the outer surface, and then after that one more conical part will come. This is the conical part. Now these channels will make a pathway for delivering the powder particles towards the molten pool. Okay, in some cases, as you have seen, lot of gas is going right towards the molten pool. Some is to carry the powder, some is to protect that, some is for shielding gas. I have seen a literature in which they used to provide then a vacuum port also, just close to just the last port. So what happened? All the unnecessary gas, those are roaming around, are taken back and then reused, just to save the amount of gas we finish in this process. Okay, so these vacuum ports just take away those gases. Then design featuring shielding gas provision for optical protection, like you are seeing here. These are the powder holding, and there is the optic shielding gas. So this particular gas will not go towards the molten pool; it will just direct like this. And as it is directing like this, it will create a curtain of the gas, which will not allow the powder particles going towards the optics to penetrate it, and hence it will push them forward. Then comes the discrete nozzles. The discrete nozzles uses multiple, usually but not limited to 3 to 4 jets of powder streams, delivering feedstock directly to the molten pool via separate and distinct powder delivery channels. The inclination of these channels with respect to each other affects the powder flow characteristics and shift the location of powder stream's focal point relative to the laser beam in both across and along the plane of deposition. The number of powder streams or channels that are participating in deposition has a significant influence on stream characteristics and consequently on catchment efficiency. So catchment efficiency is nothing but the mass flow rate or the mass going from the delivery nozzle divided by the mass of the deposited clad, okay, into 100. So study by Kolvanako et al. In 2016 demonstrate that with the increase of powder channels from 3 to 6, the particle velocity in each stream reduces. With reduction in the powder velocity, an increased clad area can be achieved, because if the powder velocity is less, it will not bounce or it will not roam here and there. Hence, you can achieve better catchment efficiency because your width of the clad is increasing. Means your cladding is now larger, and in the formula I told you, mass of the mass flow of the powder divided by mass of the clad. And if the clad is becoming larger, and of course your efficiency will increase. Okay, so for same process parameters, the condition was observed. Yeah. So now let us discuss about some design consideration of coaxial nozzle. Okay. So powder mass concentration, which signifies the number of particles per unit area of focal spot, is negatively correlated to the gas exit diameter dn and injection radius rin. Let me just show you where are they. So this is the nozzle diameter, each nozzle 1, 2, 3, whatever number is there, and this is the rin. This is the injection radius of the conical nozzle. Okay. Now, if this RIN will change, then definitely we have to increase the RDN. Sorry, DN. Fine, the diameter of the tube to achieve the same process parameters on the focal point. Also, you can see this is standard distance ST. Standard distance is the distance between this final exit point of the nozzle to the focal point. Okay, and this phi. If I increase the standard distance, what will happen? The whole thing will go like this, correct? And hence this phi will change and it will reduce. Because now, if for example standard distance is high, what will happen? The focal point will be somewhere here, and hence your angle will become something like this, correct? And you can see that the angle is reducing in that case. Correct? So alpha and SD are negatively correlated. And it is also can be seen the diameter of the nozzle will also become tiny if you are going to increase the standoff distance. Also, the injection radius that is RIN, it is directly proportional to the standoff distance. Meaning to say, if the standoff distance increases, I have to increase the RIN also, this radius also. Fine. If I'll increase this, just assuming another way, if I'm just increasing this radius, what will happen? The whole system will go here, correct? Or it will go here. And what will happen? Your standoff distance, the focal point is now here, and then again it will come here somewhere. Then of course this distance SD is increasing, right? And if RIN is increasing, the standoff distance increases. So if you why I'm telling this all, where if you are going to design your own nozzle for DED, of course all these parameters you need to be carefully designed. Another very interesting thing is, let me just put this video here. Yeah. So ensuring that we have to ensure the area of overlap powder stream is always more than the laser spot size. But you know that is the reason of low catchment efficiency. What is low catchment efficiency? Let me write this formula. The catchment efficiency says the area of the laser beam, or I should not call it as laser beam, area of the melt pool, and that is of course depending on the diameter of the laser beam, divided by the area of the powder particle or the powder stream falling onto it. Now if the area of the powder stream, that is the common area, if it is less than the diameter of the laser, of course I will have better catchment efficiency, but you are going to lose a lot of things here. I'll explain about that. It should be always like this, meaning to say where all the streams are overlapping, that region should be larger than the diameter of the laser. But in that case, the catchment efficiency will be bad, because and by visual also you can see a lot of powder is going to get waste in the environment. Now, why so it is required? You see that if the diameter is less, then of course here it will be, for example, I'm telling the 1 gram per minute is coming from this, 1 gram per minute coming from this, 1 gram per minute coming from this, and 1 gram coming from this. So in the overlap area, it will be 4 gram per minute. In these areas, it will be 3 gram per minute. And in these areas, it will be 2 gram per minute. Correct? And in a similar fashion. Now, the laser beam will then do what? More energy it will transfer to the substrate in the region where less material is available, because this is a laser beam. And if more particles are available here, less energy will be transferred to the substrate, correct? And if less material is coming, more energy will transfer. If more material is coming, less energy will transfer to the substrate, of course. Now, due to this asymmetry, what will happen? It will transfer somewhere more energy, somewhere less energy, somewhere more, somewhere less, somewhere more, somewhere less. So you will get something like this. Not desirable. Even you will get a waviness in your profile also when you deposit. It may not come like a conventional one. So, what is preferable? Preferable to have the scenario like this. Now here you see anywhere inside the laser beam, the amount of material may be 4 gram, and say it is everywhere 4 gram. And just you deposit the material, it will not make any much difference. Okay, very important. Another benefit of the discrete nozzle is that it is capable of making FGMs, functionally graded materials, not only in the Z direction. I'll ask you, you can check many researchers, lot of papers, it's easy to get published if you are dealing with 2 materials or 3 materials. What happened when you deposit one material from this nozzle and another material from this nozzle? Conventionally, in the same layer, you can't change the material. Because to change the material in a layer, first it will get mixed somewhere and then it will get delivered conventionally in the conical nozzle, I'm telling you. So what is easy? That you finish one layer with some composition. Some composition means, for example, there are two materials, copper and tool steel. Let me call it as C and let me call it as T. I deposit this particular layer with maybe 50% C and 50% T. Fine. Now the next layer I'll deposit with another composition. Fine, it is possible. You can do that. That is called the gradient in the Z direction. It is possible. But what if I want a gradient in the deposition plane? Means where I am depositing a single layer itself. And I want this change to be depending on the point. Like for example, this is the point x comma y, and I want a composition different on this xy and then next xy, next xy, all of them. For that, you need a dynamic change. You can't really wait for a while, let the powder get mixed and let it deliver. The only possibility for that is if you use multiple nozzles, they make on the spot alloy like this. I'm not saying which material is compatible, I'm not a material expert, but whatever material making alloys like this on the spot alloy can really make the XY plane functional grade materials by using discrete nozzles only. Otherwise, it will be very, very difficult. Another disadvantage of the conical nozzle is when you tilt, you know that why tilting is required. I'm sure during the process planning lecture you will learn otherwise. When you are building the part, for example, let me just take this bottle. And if you are building the part like this, there are no issues, no support mechanism is required. But if the part is tilted like this, and now I'm depositing the material, what will happen? It will fall down. So what I have to do? I have to provide support structure. But in metal, support is not usually provided. So what can we do? We have to use multi-kinematics problem, multi-axis deposition. Either we tilt the substrate like this, that is the best. But for that, you have to put the substrate on a rotary table, which reduces the area. It's not very wise decision. If you are dealing with the large, if you want to really make a large scale components. And of course, it is more efficient. You just tilt the component. But what we do, if the laser gun is mounted on a robotic arm, what will happen? The laser will move. So for example, you want to build like this, instead of the laser remain, the powder delivery device remain vertical, it will tilt like this and then deposit. Now if you are tilting it, what happens? The powder stream becomes more dense on the bottom and less dense on the top due to the gravity. And of course it will happen. We can't do anything. The solution is with the discrete nozzles. If you are having discrete nozzle, nozzle 1, nozzle 2, nozzle 3, then you can, based on the tilt, for example, you know that where you are going to tilt, you can increase the mass flow rate here. Let me call it as M3, this is M2, and let me call it as M3, the flow of the mass or the powder through these channels. Then of course in that case, M3 will be greater than M2, will be greater than M1. Otherwise, you will never get the uniform density of the powder on the cross section. With a discrete nozzle, omnidirectionality is the term which I'll discuss maybe tomorrow. Beyond 45 degree can be easily restored by simply increasing the drag velocity of carrier gas for the upper powder streams as compared to the bottom other two, that is 1 and 2. Central feed nozzles. Okay, why it is really important? Fine. So conventionally, what happened now? You are using this type of nozzles, right? In this case, what is happening? The nozzle, the powder is coming from this end and this end. So let us just try to observe why we always get this type of cross section. If you are dealing with this process, you can check, you can cut the substrate, check it, you will find this type of molten pool shape. Why it is not really rectangle? Even though if you have top hat laser beam, it's not Gaussian. Top hat means the intensity distribution is like this. It is like this. It means it is uniform distribution of energy everywhere. But still you get it like this. Why? It is because let us consider a powder particle which is marked as A and it is on its path towards the center of the molten pool. Okay, and it interacts with the laser at point X. At point X, this temperature of this particular particle A is at room temperature. So it will absorb most of the energy at this location. It will absorb a lot of energy. For example, immediately after entering and after some time after reaching here, for example, after reaching at this location, it has reached to 500 degrees centigrade. Assume that. I'm just assuming. So you see that mCp delta T is the power it has consumed already, or the energy it has consumed already. And it's quite high. Now after that, for example, after reaching this point to this point, only 100 mm is required, 100 centigrade is required. Maybe it is reaching up to only 600 degrees centigrade. Of course, it is not really much much energy, right, required for this. So the energy is decreasing. The required energy, the energy absorbed by the particle moving from X point towards the center is keep on decreasing. And if it is keep on decreasing, of course, on the available energy on the substrate will also keep on increasing. That is why the depth of the melt pool will also keep on increasing when you are moving from sides to the center. That is the reason. Now, if it is a side feeding, how the molten pool will look like? You may tell us. It will look something like this. Let me just draw it also. It will look like this. For example, I'll just fill it up. Assume that this is the molten pool, and you are not feeding from here. You are only feeding from this end. Then your molten pool will look like this. And you can check in many research also in the paper today in some Google Scholar. Go to Google and you will see the shape of the melt pool. But anyway, so what can we do? It is possible. Another advantage of using like if you use the central delivery powder, where there's a cone, right, and you are just providing energy from everywhere, you will get quite a uniform distribution of the powder material or the mold pool into the substrate. Another advantage, other than that, what we have just discussed, is the minimal divergence of the powder stream. In the case of coaxial nozzle, the recorded efficiency can be as low as up to 30%, even low, but for the central feed nozzle, the efficiency can go up to 80%. Efficiency, when I'm saying, is always the catchment efficiency. Okay, so the catchment efficiency in central feed nozzle is quite good, and this is one of the examples shown here. Okay, now let us discuss about the powder delivery nozzles and their non-pneumatic designs. Can I take 15 minutes, Dr. Onkar? Is it?
Yes.
Okay, fine. So powder delivery nozzles for non-pneumatic designs. Now this is why, first of all, why do we really need just a non-pneumatic design? It's not an academic problem. It is an industrial problem. I'll tell you how. The high velocity involved in the existing systems leads to decrease in powder catchment efficiency, along with a deteriorated surface finish of the deposited clay. The use of conveying and the shield gas increase the convective cooling, right? And you are just losing lot of energy unnecessarily by the gas. Hence, you have to use a very high power. Energy efficiency is bad. Unnecessarily, I am heating up some gas which is not of my use. Powder particles traveling with high velocity upon impacting the free surface of the melt pool generates force of sufficient high magnitude, and resulting track often shows high dilution at the center and lack of fusion at the edges. Studies also suggested the entrapment of the carrier gases into the mold pool, which leads to increase the porosity in the case of gas-based systems, and consequently a decline in the mechanical property of the parts. Of course, if the porosity will be there, the mechanical properties will be bad. The fatigue life will be really reduced, of course. I have found a literature by Wong et al. Of 2011, it's quite old as well. They perform the matrix for a non-pneumatic system and the gas assisted system. You will see now. The sample cross-section, the area is 8.60 mm square. It is more. The cladding area. The total porosity is 0.015 mm square. While in the case of gas assisted, it is more than twice. The surface roughness is around 2 micrometer, while in the case of gas assisted it is up to 14.24. It is more than around 6 times. So you see, there are benefits. There are benefits of non-pneumatic systems. And apart from that, which is not written here, there is no system for electron beam, no DET system. So if we are trying to develop a system in India, why not we develop it for the one which is not available in the worldwide? But anyway, so some popular designs here, the non-pneumatic nozzles, some popular designs are shown here. It is important to note that the most of these systems are not maintaining a concentric laser beam, although such a configuration can be devised, not the big issue. Just let us focus first on the delivery systems. So this one is what you are seeing here. I have found in the literature of by Yang et al. In 2000, in his paper of 2003. He has a aluminium block and there is a tube here. Fine, and it is filled with the powder material. They used to give the torsional vibration. Okay, you have a tube, you just do it like this, twist it. And due to the torsion, the powder is delivered through a tiny nozzle. Why it was not coming under? Because of the jamming. You know that. The arch. The powder-filled glass tube embedded inside the aluminum block vibrate torsionally using a piezoelectric. Here, the diameter T, the tube diameter, and the P diameter of the I think P, I'll let you know. I think P is written here. Let me just quickly check and come back. Okay, it's not here. I think it's powder size. The diameter of the powder is 3 to 22 micrometer. And yes, yeah, I'm correct. And also the type of powder they have tested, copper, iron, and the involved. The velocity is around 49 kilohertz. Sorry, the frequency, the torsional frequency, and the mass per second they could achieve is 0.05 to 0.3 milligram per second. It is very less, but these are only for delivering the for making the microsystems. Then there is a system developed by Chandraputra et al. In 2014. Okay, so what they did, they used to have the piezoelectric ring on the bottom side, like here. So the powder-filled glass tube vibrates with a ring-type piezoelectric again for dry powder printing. Okay, the process they call it as dry powder printing. So the tube diameter is around 110 to 400 micrometer, and the diameter of the particle, the powder particle, is 14 to 72 micrometer. The delivery rate, the mass reflow rate is 10 to 30 milligram per second. What was the issue in the previous one? The tube was locally attached with the vibratory system, right? That may break it because of the stress concentration. Another solution I found very nice one, the vibration applied through water bath. It was developed by Yang et al. In 2004. So what they did, they provide the uniform ultrasonic pulses, okay, into the water. Now this water transfer this pulse energy or the vibration to the powder delivery nozzles, right? And when the powder delivery nozzles are vibrating, they are just transferring the material on the bottom side. Now, of course, without that it will not happen because of the arch formation and all. So the tube diameter here is 280 micrometer. It's quite less still, 0.28 mm. Diameter of the powder is 12 micron, and the frequency by which they were able to vibrate it is up to 20 kilohertz. Of course, they were able to achieve the mass flow rate of 0.05 milligram per pulse in each pulse. Okay, fine. So next one is the ultrasonic. Okay, the acoustic waveform generator, they are attached like this, and due to the acoustic vibration, they are vibrating the powder tubes or the powder tubes where the powder particles can flow. These acoustic vibration imparted by subwoofers to the capillary tube via a rigid connection. Threshold amplitude is about 15 micrometer. The tube diameter is about 380 to 600 micrometer, 0.3 to 0.6 mm. While the powder diameter they are able to use is up to from 63 to 200 micrometer, and they have tested with copper and S30. The frequency they have used is around 50 to 300 hertz, and the mass flow rate is 5.8 to 35 milligram per second. This is another system. Now this is the easy one. Basically, they used to provide the vibration in the x direction and y direction by using just the piezo electric materials, right? So two piezoelectric transistors are providing horizontal and vertical vibrations to the powder dispenser. A surgical hypodermic needle acts as a nozzle. So you have seen that nozzles used for surgery. They are delivering the powder through that. And of course, the tube diameter, the opening of this tube is approximately 0.2 mm. That is 200 micron to 350 micron. So you can deliver the powder even through that tiny tubes of the syringe. Of course, the powder particles should be very, very fine in that case. That is here 10 to 90 micrometer, and the frequency was up to 20 kilohertz. The mass flow rate is 1.25 to 5.80 milligram per second. The next setup here, what you are seeing on the right side, is centrally placed piezoelectric vibration, where this center tube, what you are seeing, this one, it moves up and down. This one. Yeah, I think I saw a question. Should I take the questions in the end? Is it okay?
Yeah, you can take at the end.
Okay, thank you. So in the centrally placed piezoelectric vibration, the center portion is vibrating, the entire one. And as it is moving up and down, it is increasing or decreasing this area. And hence, it can allow the powder particles to flow towards the wall, the side walls. Here, the tube diameter is approximately 0.6 mm. The powder particle is approximately 40 to 150 micrometers, and the frequency approximately 20 kilohertz, mass flow rate 120 milligram per second. So powder delivery nozzles stream characteristics a little bit above. Usually, when you are designing your own nozzle, that is important at that time, we get a uniform, the Gaussian distribution of the powder. And when do we call it as a Gaussian distribution? It follows the 1 by square rule. 1 by square rule means the powder stream's spot radius at the focal point or the focal plane is determined by the location at which the powder density is reduced by 1 upon E square. Fine. And this is how it looks like. So these are some results of actually my nozzle. I am just putting it here, and you see that here you can find out the value of that diameter, maybe here or here, wherever, where the density of the maximum is reduced by E square, divided by E square. Wherever it is coming, that I will call as the diameter of my focal point. Now let us conclude it. First, let me just summarize. So it may be important for the one who is developing this type of nozzles. The first one is here. First, I'm trying to show you the process parameters for different systems available in the literature. So far, what we have discussed were most of the commercial systems, not the non-pneumatic ones. Non-pneumatic, I have not found any commercial one, but the other ones, the pneumatic ones, most of them are commercialized. But here there are some laboratory setups I am just explaining. Serial number 1 is the 500 watt. They uses the 500 watt laser, and they uses 4 jet discrete coaxial nozzle. The parameters like the tube diameter, alpha is the cone angle, and F is the focal point from this from the outer when the material exit, or in other words, I should call it as standard distance. The distance between the nozzle tip and the focal point. These are the parameters. They use in conal, and they use the carrier gas with a flow rate of 4 liter per minute, and the scanning speed is around 10.50 mm per second. The dimension of the track is approximately 0.1 to 0.4 in height and in width 1 to 1.4. In a similar fashion, there are other systems available. For more details about the systems, you can refer to I think one of my journals published in last year in additive manufacturing. So that part I'll skip and just quickly go to the conclusions. Powder injection angle. A low powder injection angle supports a longer depth of focus, of course, consequently promoting an increase of a range of passive stability and high deposition efficiency. Mask flow rate is often associated with increased surface roughness and track porosity. Okay, we should avoid to have high mask flow rate in many of the cases. However, it is many times desirable also to deposit with the high deposition rate, but we have to be very, very careful. Otherwise, we will end up with having more porosity. The particle velocity, we have seen that lower particle efficiency, powder velocity give us better catchment efficiency. Otherwise, lot of issues are there. The powder comes, it may bounce off. It can go here and there, and the catchment efficiency will lost. So low powder efficiency is good one. Feedstock selection, of course, the reflective materials such as the aluminum and copper are difficult to process using the conventional IR lasers as compared to the shorter wavelength lasers. The melt pool size of the conductive material such as copper attribute to its high thermal conductivity is fairly small, thus necessitating a smaller focal point of the powder stream. Otherwise, your catchment efficiency will be very bad. The powder characteristics at the focal point spot, the powder particle concentration follows a Gaussian trend, which implies the validity of 1 by E square rule to determine the size of the spot diameter. Ideally, the spot size of the powder stream should be smaller than the melt pool dimension to ensure high catchment efficiency. Shield gas, of course, the primary job of the shield gas is to prevent the melt pool to get oxidized, but often an additional gas is provided to protect the laser optics. Okay, or the metal fumes, those are generated. The metal fumes also try to go towards the optics, they also destroy the optics a lot. So that also has to be avoided. Then, of course, the omnidirectionality. This part we are going to discuss tomorrow in detail. But let me just tell what is omnidirectionality in brief today. Lateral feed nozzles are non-omnidirectional. Why they are, I'll discuss tomorrow. And primarily find application in only cladding on the rotary jobs where you are not going to change the direction of the deposition. Coaxial nozzles are omnidirectional and are employed for part fabrication through additive manufacturing, because in additive manufacturing you never know where are you going to move. You go straight, go take a turn. It depends on the data you are getting by the slicing. Smart powder delivery system is something required nowadays, because fabrication of smart powder delivery system requires a closed loop feedback control with multiple inputs to adjust its feed parameter in accordance with the that is required for the system. Similarly, the gas-free powder delivery system is really a need of ours. Since the use of electron beam requires a vacuum environment, carrier gas cannot be used for powder stroke handling. This necessitates the development of gas-free powder delivery nozzles in conjunction with the electron beam as a heat source. It can be noted that is why you have seen the EV system by CRT, they uses only wire. And if anyone, if you have any details on the system, please share with me also. So with this, I'll stop here. Thank you very much. Let us discuss. We have around 15 minutes left. So thank you very much.
Yeah, thanks, Dr. Sajan. Yeah, I think if any of you have any questions, you can unmute and ask questions one by one, or you can also post it in the chat box. I'll just read it out. So we have a couple of questions. First is from Hema Chandra. Can we know the books or any texts which we can get this information? So is there any textbook which specifically talks about these?
No, unfortunately.
Yeah.
No. So, but I think I should give that information. I'll share the details of my MOOC course, which is going to start from next month, I think in August. So there I have dedicated lectures based on this type of where I talk a lot about the system side of the 3D printing, not the process side. And I used to cover it in that manner. I'll share the detail in the end.
Okay. There's one more question.
This particular, I'm sorry to interrupt. This particular information you can get it in my research paper published in additive manufacturing last year. in the additive manufacturing journey.
Okay. So yeah, moving to the next question, the Dr. Virendra Kumar is asking, what are the parameters deciding powder size?
Okay, so the tube diameter is the major one, because if the powder particles are of larger diameter, there may be chances of clogging. And if it is like really large, another issue comes that we have to wait till the powder get melted. Why we use powder with less diameter? The one reason, very important one, is high surface area availability. Because if the powder particles are small, surface area will increase, and you know that if surface area will increase, the more energy will get absorbed. Q equals to mcp delta T. We all know that. So m is nothing but rho into volume, where volume is nothing but area into whatever. So area is there, right? That area, that is surface area. If that increases, you get more, less time required to transfer the energy. The area is more if you have a big ball, and of course, more time will be required to transfer the energy. Hence, the powder will not at all get much heated up in the laser beam, and will take more energy from the melt pool, and the RA value will not be good in that case. So I'll just say maybe three things you remember: maybe the energy available with you, the roughness you are going to get on the deposition, and the delivery nozzle. These three things can decide the size of the powder.
Sir, I have one doubt.
Yes, sir.
Hello.
Yeah.
Yes,
Yeah.
Sir, if you mix two powder like copper or aluminum or steel, then how can sir mix? Because sir, their melting point is different. So how can we get a uniform melting temperature for both?
Okay, if you are asking me from the system side, yes. What is the vaporization temperature? I mean, to make this, you can heat it up. For example, if you have copper, you have steel, you require minimum 1500 degrees centigrade. What will happen at 1500 degrees centigrade with copper? Copper will still remain in liquid form, right?
Yes, sir.
So it means both are in liquid form. Now, I already told, the mixing, making alloy or not, that I'm not the expert. So for that, some metallurgist will be required. But I can tell you, yes, if they both are in liquid form, minimum temperature 1600 degrees required. Copper will be in liquid, steel will be in liquid.
But sir, there will be chance of some vaporization of copper.
What is the vaporization temperature of copper? I don't think it is 1500 degrees.
Sir, in case the melting point of copper is 950, okay. So then maybe there may be chance of at 1500 there may be chance of some vaporization of copper.
No, it will happen only after vaporization temperature. I'm not sure how much it is, but if you know, please check if it is. Yeah, if it is like, of course, if it is 1500 degrees centigrade, but I'm sure it is not. If it is there, yes, you should not exceed that. Then in that case, your powder particle of steel will remain just suspended, and you will end up making like powder. I'll say copper matrix and powder composite. You may not be able to make the. You are right, but you need to check the vaporization temperature. I believe it will be just what do you call, super critical, but not like it will not vaporize. I think at 1500 degrees centigrade.
Okay, sir. Thank you.
Okay. Any other questions? Anyway, Dr. Sajan will have another session tomorrow during the same time, where he will continue with this omnidirectionality aspects. So we can continue with, if you have any other questions, maybe we can continue tomorrow. Okay. I think with that, I would like to thank Dr. Sajan Kapil for having this engaging session. So it was really a very insightful session on the how to decide the nozzles, what are the aspects which we need to consider. Yeah, I think maybe people can note down this. It would be
Yeah.
useful for people who are interested in more details about this. And
So
this they can also register, right, if they are interested.
yes, registration is still on. Yeah.
Okay. Yeah, that's a useful information. So if people who are really into this type of work, definitely they should look up for this course. Okay, so I think with that we come to the end of this session. So once again, I thank Dr. Sajin Kapil for having this session, and looking forward to his next session tomorrow. Uh, so yeah, I think now just some um, administrative things. I would like to just check with our volunteers if the attendance is taken um, for this session. Uh,
Taken, sir.
it's taken, no? Okay.
Yes, sir.
So yeah, I think what I would like to do is maybe if one second again. Okay. So for whoever it is possible, if they can come on their videos, if they can switch on their videos just for few minutes. We would like to have some brief, like say, plan for coming days. Okay. So
Am I required, Dr. Onkar? Just wanted
yeah,
to
you
know.
can leave, Dr.
Okay,
Sajan.
thank you.
So
Thank
yeah,
you. Thank you, Dr. Onkar.
yes,
Okay.
thanks.
Thank you, everyone. Bye.
So yeah, nice to see you all. Otherwise, uh, it's a very uh, what you say, faceless medium where you don't know to whom you are talking and who are listening to you. It's good to have to see some uh, images in front of you rather than having all these boxes. See, one thing which I would like to see, because it's an 8 day event. Normally what happens is when people are there on campus, and if we are doing some activity on this, uh, most of the you will be engaging with the uh, speakers, and you can ask questions and all. But many a times what happens is also the peer learning, the interaction with your co-participants, and then and especially the event like this where you see that, like, from north to south, east to west, we have representatives, and it's truly a pan India presence here. uh, this will also foster some kind of a collaboration, or some kind of a learning among the participants also happens in these type of events, but that is something which is not happening in a platform like this. So see, going forward, see, today and tomorrow, these are more like theoretical aspects, where I'm sure, if even if you want to set it up a DED type of system in your place, or if you have something, it is well and good, but it's very difficult for you to venture into any of these kind of systems. But going forward, the plan is to um, cater to something which you can actually replicate in your own institutions. So that is the overall plan, and that is where we also get into a lot of hands-on things. Okay, and as part of that, we are also planning to have a hands-on session where you will be working on essentially, more or less, most of you are comfortable with any CAD modeling paradigm. So we are planning to introduce one more paradigm, which is again a offshoot of what earlier they used to know, we used to know as CATIA. So CATIA is a 3D modeling software, and of course the parent company Dassault Systems have other solutions related to not just CAD modeling, but also other activities which are done in any industrial scenario, which we also talked in the morning about these PLM, product lifecycle management, and Industry 4.0, and uh, they also have specific modules which are related to 3D printing, like say design for additive manufacturing and topology optimization and things like that. So that is where we will be doing some hands-on exercise where we will be modeling some simple components just to learn or get used to the software platform. And then later on, as we move forward at the end, I would like to see at least some of you picking up this tool, or if you already have some understanding about certain tools which you are comfortable with. And I'm sure most of you might have at least done some very straightforward 3D printing where you just create a 3D model and use some FDM or any other 3D printers and then print the 3D models. So that is the plan as of now. So since this today and tomorrow, though they are also weekends, and also these are the initial 2 days of the workshop. These are more based on the theoretical aspects, where we have lectures and things like that. But starting Monday we will have some lectures, some um, hands-on where you will have to do something on the tool. So for that I would like to know, like, how many of you have a decent configuration laptop or a desktop. Okay. Essentially, for a CAD system, you need a slightly higher RAM and a good processor and things like that. But the one which we are trying out now is it's more of a cloud-based license and cloud browser based modeling paradigm. So where you can just open the software in any browser like Chrome or Internet Explorer, and you can start doing the 3D modeling. So we will see how convenient it is, because it is also a new experience for us also, to see how uh, people from all over the country spread out and they are using same software paradigm. There are many other aspects which can be leveraged to a greater extent if we stay with this, because this software has a capability to seamlessly share the information which essentially forms the part of PLM framework. So these things will be discussed first in a theoretical setting, and then we will share the licenses with you, and you can actually register. I think already some of you might have already received the emails for registering on the 3D experience platform. So, but till now we have not received the final licenses from Dassault Systems, and as soon as we receive, hopefully by Monday, we are planning to get that. But as and when we get, at least there will be hands-on tutorials. You can practice those tutorials, exercise using the software. And ideally what I want you to do is maybe uh, either individually, or you can also form a group among yourself, and let us see, because that at least will bring in some of you together, and make sure that you don't of course I don't see anybody from the same institute, even though there are multiple representatives from different states of India. So at least I want you to partner with somebody, maybe a group of two or three or whatever you are convenient with, and develop some new concept as part of this. And then, like morning, even Guru Prasad and Professor Surya, they were sharing, no, like there are these complex mathematical shapes which can be explored, or any other novel geometrical shapes you would like to develop as part of this. And at the end of the course, and then if you can model it and share it with us, we can actually 3D print and send it back to you. Okay, so that is something which brings a kind of a complete completeness to the whole workshop, where from your idea, how to transform these ideas into a digital representation, and then how do you consider the manufacturing aspects? of course, right now we are not going to do anything in metal or even polymer, sorry, these liquid resin and things like that. Mostly we will be working with FDM type of processes. But in case if you come up with a concept which requires any of these things, we can still explore that. Okay. As such, facility wise, IIT Hyderabad has all the type of 3D printing technologies, starting from resin to bio, metal, and then color printer, and all type of 3D printing technologies. Yeah, at least whatever the major 3D printing technology, including weld-based deposition, DED, and things like that. So we will see if it requires that kind of a facility, because it also depends on the cost. There is a material cost involved and things like that. But we can easily work with anything related to FDM and plastic-based components. So that is the idea which I am trying to develop through this workshop, and see how best we can deliver this content. And as also in the morning when Professor Suhash was discussing, like if we can see, ultimately the goal of this workshop is to replicate this model. And we had a uh, similar experience earlier, because this module, this 8-day module, we had a shorter version of a 5-day module which we had delivered sometime in the month of November. And based on that, this I think from um, uh, I remember from Pune, College of Engineering Pune, COEP Pune, they had actually come up with their own workshop. So they started having a workshop for their students and their faculty, and then they had asked some of us to come and have some sessions in their training program. So that is how we would like to see this disseminating to the next levels, and then see how best it can benefit the students in all the engineering colleges. So with that intention, maybe if you have any ideas or anything to share, you can always share it with me. But either individually or as a group, if you can develop something which is interesting, where you can at the end of the workshop, if you can showcase as a something which you have done as part of this, that would be really interesting to uh, take it forward. And in between we will also have supporting hands-on sessions, where you will be actually trying out some of these things using the whatever the CAD platform which we are experimenting. Okay. So I think, yeah, I am also looking forward to that. This is first time we are trying out in a distributed fashion, where different people working in different places will be using a CAD software in a browser, and we really don't know what is the speed and how seamlessly we will be able to perform the modeling task. But yeah, that is the overall plan. And if you also look at the other activities, uh, there are speakers from different and many other domains of 3D printing. See, 3D printing is not just a manufacturing of some metal components or some plastic component. There are newer ways of implementing these 3D printing techniques. So as far as possible, we try to cover all possible domains. We have faculty who are working in bioprinting, biomaterials, and material characterization, where there are 3 or 4 people who are from material science and metallurgy department, who will be talking about the particles, metal powder, and the characterization of materials and composites, and how 3D printing can be Professor Surya was also mentioning this Mark Forge system, which basically it produces a composite 3D printed components. So these type of things, there are individual experts who will be talking about these specific aspects, and in general there are also other aspects like construction, printed circuits, and so the applications are very vast, and though the technology is very focused on the layer by layer type of manufacturing, but the way it has been applied by different people uh, for different type of applications, that is what that whole gamut we are planning to cover, and I hope it will give you a broader perspective on this whole 3D printing technology. Okay, so I think with this, I would like to conclude today's sessions. And tomorrow morning, again, we will be starting uh, with the session with Professor Surya, and we will continue with this. So I think again, Surya, Guru Prasad, and Dr. Sajan, they will be repeating this. Means basically, they will be continuing their sessions, and also Dr. Rajesh from material science, he will be talking about the material characterization. So since today and tomorrow are more of a theory and more of a lecture based events, so we will try to finish with this, and then Monday we will start with the hands on activities. Okay, so in case if you have any queries or anything you would like to add, yeah, morning, some of you have shared very interesting suggestions, so I'll definitely look into that, and we will try to address those things. Okay, so yeah, I think with that, thank you, thanks for attending all these sessions, but yeah, so there is a some kind of a requirement from the NPIU, where we need to send the attendance and things like that. So make sure that you be present. Of course, there is a software version of that, because basically in Webex itself, it records all the names and the timing for which the people have attended and things like that. So, but anyway, some of our student volunteers will be taking attendance based on the names which they appear in the participant lists. Okay, so make sure that you are present throughout the sessions, and then and hope it is of some benefit to you. And we'll continue tomorrow then. Okay, thank you. Have a good day. See you tomorrow morning. Okay.